something out there is breaking the rules of the universe. A flash of blinding blue light erupts in space, burning hotter than almost anything we've ever seen, then, just as suddenly, it vanishes. It's faster than a supernova, brighter than an ordinary star explosion, and completely unpredictable. Scientists have no idea what's causing it, but one thing is clear: these mysterious bursts should not exist. And yet they do. They're called luminous fast blue optical transients, and they might be the strangest cosmic events ever discovered. But before we continue, subscribe to the channel so you don't miss out on any of these videos. These bizarre bursts of light are some of the most unexplained cosmic events we've ever come across. They don't behave like supernovae, they don't match any known gamma ray bursts, and they happen in places where no one expects such explosions to occur. In other words, LFBOTs don't follow the rules. They appear suddenly, last only a brief moment, and then fade away, leaving behind almost no trace. The first time scientists discovered one, they thought it had to be some kind of mistake. But as more and more of these flashes were detected, it became clear that something truly strange was happening in the universe. To understand why LFBOTs are such a big deal, we need to break down what makes them so different from everything else we know about space explosions. When a star reaches the end of its life, it usually follows a few predictable paths. It might collapse into a black hole, explode into a supernova, or turn into a neutron star. But whatever happens, it follows a pattern we can study and predict. LFBOTs, however, throw all of that out the window. They burn hotter, fade faster, and appear in places where there shouldn't be enough material to fuel such an intense explosion. Take the first well-documented LFBOT, discovered in 2018. Scientists originally classified it as a supernova and named it at 2018 Cal, yes, the Cal. But there was nothing ordinary about it. It shone 100 times brighter than a normal supernova and faded away far too quickly. Within days, its brightness plummeted, something that shouldn't happen with typical star explosions. To make things even weirder, it emitted high-energy X-rays and radio waves, suggesting that something incredibly energetic was happening inside. At first, researchers thought maybe this was just a really weird type of supernova, maybe a star that collapsed directly into a black hole while still somehow managing to blast out a massive burst of energy. But then, more LFBOTs started popping up, each with its own strange properties. They weren't just rare supernovae, they were something entirely different. And the more scientists looked into them, the more questions they had. One of the biggest mysteries surrounding LFBOTs is their location. Normal supernovae usually happen in large galaxies, where there are plenty of stars ready to explode. But LFBOTs? They don't care about the rules. Many of them appear in the middle of nowhere, far from any galaxy, where there shouldn't be enough gas or dust to fuel such a violent explosion. This has led some researchers to wonder if we're dealing with an entirely new type of astronomical event, something that doesn't fit into any existing category. Another strange thing about LFBOTs is the way they behave across different wavelengths of light. When scientists study cosmic explosions, they look at all kinds of signals: visible light, X-rays, gamma rays, and even radio waves. Most known events have a predictable pattern. But LFBOTs don't just shine in one spectrum, they fire off bursts of energy in all directions, across multiple wavelengths, as if something incredibly chaotic is happening at their core. Some theories suggest that LFBOTs could be the birth cries of black holes, events where a massive star collapses so quickly that it doesn't just form a black hole, but also sends out an enormous blast of energy as the black hole rapidly devours the surrounding material. Others think they could be neutron stars undergoing some kind of extreme process that we've never seen before. And then there's the possibility that LFBOTs might be linked to something even more exotic, like Magnetars, ultramagnetic neutron stars that can unleash bursts of energy so powerful they can be detected across the universe. But even these theories don't fully explain what's going on. The problem with LFBOTs is that they're just too fast and too powerful. A normal supernova takes weeks or even months to reach peak brightness. LFBOTs do it in a matter of days. And while gamma-ray bursts can also be incredibly fast, they usually happen in very specific conditions that LFBOTs don't seem to follow. What makes all of this even more frustrating for scientists is that LFBOTs don't leave behind the kind of evidence they need to study them properly. When a star explodes in a normal supernova, it leaves behind a nebula, a black hole, or a neutron star, something that researchers can observe and analyze. But LFBOTs? They just disappear. They shine bright, fade away, and leave almost nothing behind. It's like they're breaking the fundamental rules of physics, and no one knows why. One of the most mind-blowing possibilities is that LFBOTs could be connected to something entirely new, some kind of astrophysical event that we haven't even imagined yet. What if they're not just exploding stars, but something even more extreme? Some scientists have even speculated that LFBOTs might be signs of things like failed black hole births, collisions between exotic objects, or even new types of cosmic matter that we've never encountered before. The mystery of LFBOTs isn't just about figuring out what they are, it's about understanding what they mean for our knowledge of the universe. If these events are truly unique, it means there's a whole new category of cosmic phenomena out there that we've only just started to uncover. And if that's the case, then what other secrets could be hiding in the depths of space, waiting to be discovered? If LFBOTs really are a completely new type of cosmic event, it raises an even bigger question: how many of these have we missed? Space is vast, and our ability to detect these flashes depends on having telescopes looking in the right place at the right time. LFBOTs don't last long. They peak in brightness in just a few days and fade quickly afterward. That means if we're not constantly scanning the sky, we could be missing dozens, hundreds, or even thousands of these events happening all the time. And that's where things get even more exciting. With newer, more advanced telescopes, like the Vera C. Rubin Observatory, set to come online soon, scientists expect to find even more LFBOTs in the coming years. This could finally give us the data we need to crack the mystery wide open. But there's still a huge challenge. Even if we detect more LFBOTs, we need to figure out where they're coming from and what's causing them. And so far, every new discovery has only deepened the mystery. One of the strangest things about LFBOTs is that they don't seem to fit neatly into any existing astrophysical models. They're too bright to be normal supernovae, but they don't last long enough to be traditional gamma-ray bursts. They emit high-energy radiation, but not in the way we'd expect from known cosmic explosions. And their locations make no sense. Some appear in galaxies, while others happen in the middle of nowhere, in regions where there shouldn't be enough material to fuel such an intense burst of energy. This has led some researchers to propose some truly wild theories. What if LFBOTs are connected to some kind of exotic astrophysical object that we don't yet understand? Some scientists have speculated that they might be linked to strange, ultra-dense neutron stars known as Quark stars, hypothetical objects made entirely of subatomic quarks, which could produce bursts of energy unlike anything else we've ever seen. Others think LFBOTs might be the result of massive collisions between compact objects, like black holes or neutron stars, creating a brief but powerful burst of energy before disappearing completely. But here's where it gets even crazier. What if LFBOTs aren't natural at all? Some have speculated, purely as a thought experiment, that they could be signs of advanced alien civilizations harnessing extreme cosmic energy sources. It might sound like science fiction, but when we're faced with phenomena that don't fit into our current understanding of physics, we have to consider all possibilities. Could LFBOTs be the result of some kind of artificial cosmic engineering, maybe an advanced species manipulating stars, black holes, or other high-energy astrophysical processes for unknown purposes? Of course, the alien hypothesis is pure speculation, and most scientists prefer to focus on natural explanations first. But even within the realm of known physics, LFBOTs challenge everything we thought we knew about how stars, galaxies, and high-energy explosions work. Every time we think we're close to figuring them out, a new discovery throws us right back into confusion. For example, in 2023, astronomers detected an LFBOT that didn't just emit optical light but also produced powerful X-rays and radio waves, behaving in ways that had never been seen before. It suggested that whatever was causing these bursts wasn't just a single explosion but might involve an ongoing process, something that kept generating energy even after the initial flash faded. That's completely different from how supernovae behave, which suggests that LFBOTs might be an entirely separate class of astrophysical events. Another major challenge is understanding the energy source behind LFBOTs. For something to shine that brightly in such a short amount of time, it has to release an enormous amount of energy, far more than a typical supernova. But where does that energy come from? Some scientists believe that LFBOTs could involve Magnetars, ultramagnetic neutron stars that can produce massive bursts of energy. If a Magnetar formed under just the right conditions, it might create a flash similar to what we see with LFBOTs. But even this theory doesn't explain all of the observed features. So far, every new piece of data has only made LFBOTs more mysterious. The fact that they appear so suddenly, burn so brightly, and then vanish without a trace makes them one of the biggest astrophysical puzzles of our time. And the implications are huge. If we can figure out what's causing LFBOTs, it could change our entire understanding of high-energy physics, the life cycle of stars, and even the fundamental nature of matter itself. And that brings us back to the biggest question of all: what are LFBOTs, and why do they exist? Are they rare, once-in-a-lifetime cosmic accidents, or are they a common but previously unnoticed phenomenon? Are they related to black holes, neutron stars, or something else entirely? And perhaps most importantly, what do they tell us about the universe? We may not have the answers yet, but one thing is certain: LFBOTs are a reminder that space is still full of mysteries waiting to be uncovered. With every new telescope, every new observation, and every new discovery, we get closer to understanding the true nature of these bizarre, unexplained flashes of light. Until then, all we can do is keep watching the sky, because somewhere out there, at this very moment, another LFBOT might be bursting into existence, challenging everything we thought we knew about the cosmos. If there's one thing we've learned from the history of astronomy, it's that the universe has a way of surprising us. Every time we think we have a complete understanding of how things work, a new discovery comes along that forces us to rethink everything. Luminous fast blue optical transients, or LFBOTs, are a perfect example of this. They don't behave like anything we've ever seen before, and no existing theory fully explains them. They challenge our assumptions about how stars die, how matter behaves under extreme conditions, and even the very nature of high-energy astrophysical events. But maybe the most mind-blowing part of all this is the possibility that LFBOTs could be revealing an entirely new class of cosmic phenomena, one that we've only just begun to uncover. Think about it, just a few decades ago, we didn't even know that fast radio bursts, FRBs, existed, and now they're one of the biggest mysteries in astrophysics. Could LFBOTs be another breakthrough, leading us to a deeper understanding of the universe? One of the biggest clues we have about LFBOTs comes from their extreme brightness. These events outshine entire galaxies for a brief moment, suggesting that whatever's causing them is releasing an absolutely insane amount of energy. To put it into perspective, a single LFBOT can release more energy in a few days than our Sun will produce in its entire lifetime. That kind of power isn't just rare, it's almost impossible to comprehend. And here's where things get really strange. LFBOTs don't just emit visible light. Some of them also give off X-rays, radio waves, and even gamma rays, suggesting that they involve highly energetic processes happening across multiple wavelengths. But the weirdest part? Unlike supernovae, which occur in predictable locations within galaxies, LFBOTs sometimes appear in the middle of nowhere, far from any known stars or galaxies. This has led some scientists to wonder, what if LFBOTs aren't just rare? What if they're the result of something completely unknown, something we've never even considered before? One possibility is that LFBOTs are the signatures of previously undetected cosmic collisions. Imagine two neutron stars colliding at nearly the speed of light, producing a burst of energy unlike anything we've ever seen. Or perhaps they're the result of a black hole suddenly tearing apart a star in an event known as a tidal disruption event, but with a twist. Maybe these disruptions involve ultramagnetic environments that create never-before-seen bursts of light. Another theory suggests that LFBOTs could be related to the birth of Magnetars. Magnetars are neutron stars with magnetic fields so strong that they could literally tear apart atoms at a distance of thousands of kilometers. If an especially massive star collapses into a magnetar under the right conditions, it might produce an LFBOT as a side effect. But even this idea doesn't explain why LFBOTs happen so suddenly, or why they're so much brighter than expected. And then there's the possibility that LFBOTs are connected to dark matter or other exotic physics. Could they be the result of interactions between normal matter and an unknown form of dark energy? Could they be linked to quantum scale processes happening on a cosmic scale? We don't have the answers yet, but every new LFBOT detection gives us more data to work with, and with more data, we get closer to solving the mystery. But here's the big problem. Because LFBOTs are so short-lived, they're incredibly difficult to study. Unlike supernovae, which can remain visible for weeks or months, LFBOTs flash into existence and then disappear in just a few days. That means scientists have to act fast. If they miss the initial burst, they might not get another chance to study it. This is why astronomers are now setting up dedicated observation programs designed to catch LFBOTs in real time, using automated telescopes that scan the sky for sudden changes in brightness. And what if we could not just observe LFBOTs, but actually predict them? Right now, we have no way of knowing when or where one will appear. But if we could identify patterns, maybe certain regions of space where LFBOTs are more common, or specific conditions that lead to their formation, we might be able to anticipate them before they happen. That would allow astronomers to prepare in advance, positioning telescopes and satellites to capture every detail of the event as it unfolds. Some researchers have even suggested that artificial intelligence could help in this effort. By training AI systems to analyze vast amounts of astronomical data, we might be able to identify subtle signals that precede LFBOTs, small changes in light, energy fluctuations, or other hidden clues that could act as early warning signs. If this works, we could revolutionize our ability to study these events, turning LFBOTs from unpredictable mysteries into predictable, repeatable phenomena. But even if we solve the puzzle of LFBOTs, the implications go far beyond just understanding these mysterious flashes of light. If LFBOTs really are connected to unknown physics, they could give us new insights into some of the biggest questions in science. Questions about how matter behaves under extreme conditions, how energy is transferred across the universe, and even the fundamental forces that shape reality itself. And there's one final, unsettling possibility. What if LFBOTs are just the tip of the iceberg? What if they're just one example of a much larger category of cosmic events that we've never seen before? If that's the case, then studying LFBOTs might not just solve one mystery, it might open the door to an entirely new field of astrophysics, one filled with even bigger, even stranger discoveries. For now, all we can do is keep looking up. Somewhere out there, in the vast depths of space, another LFBOT is about to ignite, shining for just a moment before fading into darkness. And when it does, it will leave behind another clue, another piece of the puzzle waiting to be solved. The more we learn about LFBOTs, the more it seems like they are unlike any other known cosmic event. The speed, intensity, and location of these bursts challenge almost every existing theory in astrophysics. Some scientists argue that they might be related to extremely rare types of supernovae, but even that doesn't fully explain their bizarre properties. The fact that they appear in places where stars are not supposed to be dying makes it even harder to classify them. One of the biggest mysteries about LFBOTs is their rapid rise and fall in brightness. Most cosmic explosions follow predictable patterns. They start out bright, fade slowly over time, and leave behind traces that can be studied for years. But LFBOTs don't behave this way. They erupt suddenly, reaching peak brightness in just a matter of hours, then fade away much faster than expected. This suggests that whatever is causing them is not just an ordinary stellar explosion, but something far more extreme. To make things even stranger, LFBOTs emit high-energy radiation that doesn't match typical supernovae. Some observations have detected powerful X-ray and radio bursts accompanying these optical flashes. This could mean that LFBOTs are somehow linked to black holes or neutron stars, but if that were the case, we would expect them to appear in regions with a lot of massive stars, and yet they don't. Some have been detected in the outskirts of galaxies, where star formation is minimal. Could this mean that LFBOTs are the result of something exotic, something we don't even have a name for yet? Some astrophysicists have proposed that these events might be caused by collisions between objects we've never directly observed, such as free-floating black holes, rogue neutron stars, or even hypothetical objects like quark stars. Quark stars are theoretical objects that are thought to form when a neutron star collapses even further, compressing matter into its most fundamental particles, quarks. These stars would be incredibly dense and unstable, and some scientists believe that if they do exist, they might occasionally undergo violent explosions that could produce something like an LFBOT. But this is purely speculative, as no quark star has ever been observed. Another possibility is that LFBOTs are somehow linked to gamma-ray bursts, GRBs. GRBs are some of the most powerful explosions in the universe, thought to be caused by the collapse of massive stars or the collision of neutron stars. But GRBs usually have a different signature. They emit bursts of gamma rays, followed by an afterglow that lasts much longer. LFBOTs, on the other hand, seem to be much shorter and produce different types of radiation. Could LFBOTs be a special kind of gamma-ray burst that we haven't identified before? Or are they something entirely separate? Some researchers have even suggested that LFBOTs could be signs of failed supernovae. A failed supernova is a scenario in which a star reaches the end of its life, but instead of exploding in a traditional supernova, it collapses directly into a black hole. In some cases, this process might produce a brief, intense burst of energy before the star completely vanishes. If LFBOTs are related to this process, they could be offering us a rare glimpse into one of the most mysterious phenomena in astrophysics, the birth of a black hole. But here's where things get even weirder. Some LFBOTs have been observed producing bright, energetic outbursts long after the initial flash. This suggests that whatever process is causing them isn't just a one-time explosion, it might be ongoing. Some scientists speculate that LFBOTs could be powered by rapidly spinning Magnetars, which release bursts of energy as their powerful magnetic fields twist and break. If this is the case, then studying LFBOTs could give us valuable insights into how some of the most extreme objects in the universe evolve over time. The problem is, we simply don't have enough data yet. Because LFBOTs are so rare, every new detection is a major event for astronomers. Right now, telescopes around the world are working to find more of them, hoping that with enough observations, we can start to see patterns and make predictions about where they might appear next. One of the most exciting developments in this search is the increasing use of artificial intelligence. Modern sky surveys are collecting massive amounts of data every night, far more than human astronomers could ever analyze on their own. By training AI models to recognize the unique characteristics of LFBOTs, researchers hope to catch more of these events in real time, allowing telescopes to immediately focus on them and gather as much information as possible. And what if we could go even further? What if we could build specialized space telescopes designed specifically to hunt for LFBOTs? Right now, most of our observations come from ground-based telescopes, which are limited by the atmosphere and the rotation of the Earth. But a space-based observatory dedicated to transient events could revolutionize our understanding of these mysterious flashes. By continuously scanning the sky with high-speed cameras and sensitive detectors, we might finally be able to solve the puzzle of LFBOTs once and for all. But even if we do figure out what's causing them, that might just lead to even bigger questions. If LFBOTs are linked to some unknown form of stellar collapse, what does that mean for our models of how stars evolve? If they're the result of collisions between exotic objects, could that point to new types of matter we've never detected before? And if LFBOTs really are connected to failed supernovae, what does that tell us about the formation of black holes? Some scientists have even begun to entertain more radical ideas. What if LFBOTs are signs of advanced extraterrestrial civilizations using some kind of unknown energy source? While this might sound like pure science fiction, the truth is that we can't rule anything out yet. The universe is vast, and our understanding of its most extreme phenomena is still in its infancy. Until we gather more data, we have to keep all possibilities on the table, no matter how strange they might seem. LFBOTs remind us of how little we truly know about the cosmos. Every time we think we've got things figured out, the universe throws another mystery our way. But that's what makes astronomy so exciting. The deeper we look, the more surprises we find. And somewhere out there, in the vast, endless darkness of space, another LFBOT is about to ignite, offering us another clue, another puzzle piece, another chance to unlock the secrets of the universe. But as we continue to search for answers, one thing is becoming clear: LFBOTs are unlike anything we've ever encountered. If they were just another type of supernova, we would expect them to follow at least some of the same patterns as other stellar explosions. But they don't. Their rapid rise in brightness, their sudden disappearance, and their locations in unexpected regions of space defy all conventional models. One of the biggest challenges in studying LFBOTs is that they happen so fast. Most astronomical events, like supernovae or gamma-ray bursts, give scientists at least some time to prepare observations. But LFBOTs erupt suddenly, sometimes in just a matter of hours, and fade quickly. By the time a telescope is pointed in the right direction, the event may already be over. This means we have to rely on automated sky surveys, robotic telescopes that scan the night sky for any changes. These systems have helped us detect more LFBOTs in recent years, but the mystery remains: what exactly is causing them? Some astronomers have suggested that LFBOTs could be related to fast radio bursts, FRBs, another unexplained cosmic phenomenon. FRBs are powerful flashes of radio waves that last only milliseconds, yet release as much energy as the sun produces in a year. Like LFBOTs, FRBs appear out of nowhere, and their exact cause remains unknown. While most FRBs have been detected in distant galaxies, a few have been traced to Magnetars, neutron stars with extremely strong magnetic fields. Could it be that LFBOTs and FRBs are two sides of the same coin? Could they both be caused by some exotic activity happening inside Magnetars? If that's the case, it would mean that Magnetars are capable of producing not just intense radio waves, but also brilliant optical flashes. This would completely change our understanding of how these objects behave. Magnetars are already some of the strangest objects in the universe, with magnetic fields trillions of times stronger than anything we can create on Earth. If they are also responsible for LFBOTs, it could mean that they occasionally undergo catastrophic energy releases that we've never observed before. But if Magnetars aren't the answer, then what else could be? Some scientists have proposed that LFBOTs might be the result of mergers between strange celestial objects. When two neutron stars collide, for example, they can produce an enormous burst of energy. But LFBOTs don't match the usual signature of neutron star mergers. Instead, some researchers think they could be caused by something even more bizarre: collisions between white dwarfs and black holes. Imagine a white dwarf, the dense core of a dead star, drifting through space. If it gets too close to a black hole, the immense gravity of the black hole could tear it apart in a violent explosion. This could explain the sudden brightness of LFBOTs, as the shredded material from the white dwarf heats up and releases energy. It could also explain why LFBOTs appear in unexpected locations, since black holes can drift through galaxies without being tied to star-forming regions. And then there's an even wilder possibility: LFBOTs could be caused by something that doesn't even exist in our current understanding of physics. Some astrophysicists have speculated that these bursts could be linked to primordial black holes, ancient black holes that may have formed in the first moments after the Big Bang. If primordial black holes exist, they could be colliding with stars and causing these mysterious explosions. But here's the catch: no one has ever confirmed the existence of primordial black holes. They remain purely theoretical. If LFBOTs really are linked to them, it would mean we've just stumbled upon evidence of a completely new type of celestial object, one that could reshape our understanding of the universe. Right now, astronomers are racing to collect more data. With each new LFBOT detection, we learn a little more, but the mystery remains far from solved. One of the best ways to study these events is by using multimessenger astronomy, a technique that combines different types of observations, like optical, radio, and gravitational waves. If we can detect an LFBOT at the same time as a gravitational wave signal, it could give us direct proof that these events are linked to mergers between exotic objects. But even if we don't find a gravitational wave connection, there are still plenty of other ways to investigate LFBOTs. Upcoming telescopes like the Vera C. Rubin Observatory, which is designed to scan the entire sky every few nights, could help us find more of these events and track them in real time. The James Webb Space Telescope, with its ability to see infrared light from the most distant objects in the universe, could also play a role in uncovering the true nature of LFBOTs. And what if we go even further? What if LFBOTs aren't just rare events, but actually clues to a larger, hidden aspect of the universe? Some theorists have even suggested that these bursts could be linked to exotic forms of matter, like strange quark matter or even dark matter interactions. If that's true, then LFBOTs could be pointing us toward a fundamental breakthrough in physics, something as revolutionary as the discovery of black holes themselves. But for now, we are still in the dark. Each new LFBOT adds another piece to the puzzle, but the overall picture remains unclear. And yet, that's what makes this so exciting. The universe has always been full of surprises, and LFBOTs are one of the biggest ones we've encountered in recent years. Whatever they turn out to be, whether they're linked to black holes, neutron stars, magnetars, or something entirely unknown, they are teaching us that the cosmos is far more complex and mysterious than we ever imagined. One thing is certain, the search for answers isn't over. Every time an LFBOT appears, astronomers around the world rush to capture as much data as possible, hoping that the next one will bring us closer to solving the mystery. And who knows? The next LFBOT could be detected at any moment, lighting up the sky with a burst of energy from the unknown. But the deeper we look into LFBOTs, the more perplexing they become. Some of the recent detections have shown variations that weren't expected, further complicating our understanding of what could be causing them. For example, certain LFBOTs have exhibited unusual polarization in their light, which suggests that powerful magnetic fields might be involved. This could support the idea that Magnetars are somehow linked to these events, but once again, the evidence isn't clear enough to say for certain. Another strange aspect of LFBOTs is their color. When astronomers analyze the light coming from an astronomical object, they can break it down into different wavelengths to see what elements are present and how hot the object is. LFBOTs, despite their name, don't always behave like typical blue optical transients. Some of them appear redder than expected, while others shift colors over time in ways that don't match normal stellar explosions. This hints that multiple processes could be happening at once, making it even harder to pinpoint a single cause. And then there's the matter of their energy output. LFBOTs release an immense amount of energy in a very short period of time, but the way they fade is also unusual. Most supernovae take weeks or months to dim, but LFBOTs can fade in just days. Some even appear to re-brighten briefly before fading again, as if some internal mechanism is causing them to pulse before disappearing completely. This kind of behavior is rare in astrophysics, making LFBOTs even more of an enigma. One of the most famous LFBOTs, known as that 2018 cow, nicknamed the Cow, was one of the first to be studied in detail. It exploded in a relatively nearby galaxy, allowing astronomers to gather high-quality data. But instead of answering questions, it raised even more. The Cow's spectrum showed signs of rapid material ejection, along with a persistent energy source that kept it glowing long after it should have faded. Some scientists suggested that this could be the birth of a black hole or neutron star, as if we were witnessing the exact moment when a massive star's core collapsed into something new. If that's true, it would mean LFBOTs are giving us a front-row seat to one of the most extreme processes in the universe, the formation of compact objects like black holes. But this doesn't explain all LFBOTs, as later detections have shown variations that don't fit neatly into this model. Some appear to be even brighter and more energetic than the Cow, while others fade too quickly to be explained by a black hole or neutron star formation event. One of the biggest challenges in solving this mystery is the sheer rarity of LFBOTs. Unlike supernovae, which happen frequently enough that we can study multiple examples every year, LFBOTs are much harder to find. This means we don't have a large sample size to compare them, making it difficult to identify common patterns. Some researchers believe that LFBOTs could be happening more often than we realize, but because they fade so quickly, many of them might be going undetected. To solve this problem, astronomers are turning to machine learning and artificial intelligence. By training algorithms to recognize the signature of an LFBOT in real time, we might be able to catch more of them before they fade. Projects like the Zwicky Transient Facility, CTF, and the upcoming Vera C. Rubin Observatory are already scanning the sky for unusual events, and they could play a crucial role in discovering new LFBOTs. But what if LFBOTs aren't just rare explosions, but part of a larger cosmic puzzle? Some researchers have suggested that these bursts could be connected to other transient phenomena, like kilonovae, explosions that occur when two neutron stars merge. Kilonovae release heavy elements like gold and platinum into space, but they don't quite match the brightness and speed of LFBOTs. However, if some kind of exotic merger is happening, perhaps involving a neutron star and a black hole, it could produce an explosion unlike anything we've seen before. Another possibility is that LFBOTs are linked to hypervelocity stars, stars that have been ejected from their galaxies at incredible speeds. If one of these fast-moving stars were to collide with a dense object like a neutron star or black hole, the resulting explosion could resemble an LFBOT. This would explain why some LFBOTs appear in unexpected locations, far from regions where star formation is actively happening. And then there's the idea that LFBOTs could be connected to gamma-ray bursts, GRBs. GRBs are among the most powerful explosions in the universe, capable of releasing more energy in a few seconds than the Sun will emit in its entire lifetime. While most GRBs come from the deaths of massive stars or neutron star mergers, some researchers think that LFBOTs could be a type of failed GRB, an event that almost produces a full gamma-ray burst but instead manifests as a bright optical flash. If this is the case, it would mean LFBOTs are revealing a whole new category of cosmic explosions that don't fit neatly into our existing classification system. This wouldn't be the first time astronomers have had to rethink how they categorize stellar deaths. Before LFBOTs were discovered, we thought we had a good grasp on the different types of supernovae, but now we realize there's still so much we don't know. One of the most mind-bending theories about LFBOTs is that they could be connected to exotic physics, processes that go beyond our current understanding of the laws of nature. Some theoretical physicists have even proposed that LFBOTs could be linked to hypothetical particles like axions, which are thought to interact with light in strange ways. If LFBOTs are somehow tied to axion production, they could be providing indirect evidence for new physics that could reshape our understanding of the universe. Others have suggested that LFBOTs might be the result of interactions between normal matter and dark matter. Dark matter is one of the biggest mysteries in physics. It makes up most of the mass in the universe, but we can't see it directly. If dark matter occasionally interacts with regular stars in some unknown way, it could create sudden bursts of energy that resemble LFBOTs. At this point, we're still far from solving the mystery. But the good news is that we now have more tools than ever before to study LFBOTs in detail. With next-generation telescopes, real-time monitoring systems, and collaborations between observatories around the world, we are slowly gathering more data that could lead to a breakthrough. And the most exciting part? The next big clue could appear at any moment. Somewhere out there in the vastness of space, another LFBOT is bound to erupt. It might already be happening right now, sending a burst of energy across the universe, waiting for our telescopes to catch it. And when we do, it could be the key to unraveling one of the most fascinating mysteries of modern astrophysics. But let's step back for a moment and think about what this really means. Every time we witness an LFBOT, we are essentially seeing something the universe has hidden from us for billions of years. These bursts are so brief, so rare, and so powerful that until very recently, we didn't even know they existed. This raises an important question. How many other cosmic events are happening right now that we simply don't have the technology to detect? It's a reminder of just how vast and unpredictable the universe is. Despite all the advancements we've made in astrophysics, there are still entire categories of phenomena that remain undiscovered. LFBOTs are just one example of something that challenges our understanding of stellar evolution, energy release, and the extreme conditions that exist in space. And if we've only recently uncovered these strange bursts, what else could be lurking out there, beyond the limits of our current technology? Scientists are now trying to simulate LFBOTs using powerful computer models. By recreating different explosion scenarios, they hope to figure out what could be producing these bursts. Some of the simulations suggest that LFBOTs could be the result of failed supernovae, stars that try to explode but don't fully succeed, leaving behind an exotic remnant instead. Others hint that they could come from binary star systems, where a smaller star is being torn apart by a larger, more powerful companion. But so far, none of these models can fully explain every LFBOT that has been observed. The biggest problem is the sheer variation in their behavior. Some are extremely bright and long-lasting, while others fade away quickly. Some show signs of a compact object at their center, while others do not. This means that there may not be just one cause of LFBOTs, but rather multiple different processes that produce similar-looking explosions. This wouldn't be the first time astronomers have had to rethink an entire category of cosmic events. Not long ago, fast radio bursts, FRBs, were considered one of the biggest mysteries in astrophysics. These were incredibly short, millisecond-long bursts of radio waves that seemed to come from all over the universe with no clear explanation. At first, no one knew if they were caused by neutron stars, black holes, or something even more exotic. But after years of study, scientists realized that FRBs are likely coming from highly magnetized neutron stars, known as Magnetars, which produce powerful bursts of energy under certain conditions. Could LFBOTs follow a similar path? Right now, they seem just as mysterious as FRBs once were. But with more data, more observations, and more advanced models, we may eventually uncover their true nature. And when we do, it could change our understanding of high-energy astrophysics forever. One of the most exciting aspects of studying LFBOTs is the possibility that they might be linked to something we haven't even imagined yet. What if these bursts are connected to some unknown form of stellar death? What if they are a completely new class of cosmic event, one that doesn't fit into any of our existing categories? It's entirely possible that LFBOTs represent a missing piece of the puzzle in our understanding of how the universe evolves over time. And this brings us to an even more mind-bending possibility. What if some of the assumptions we've made about how stars live and die are wrong? Right now, we classify stellar deaths into a few main categories: supernovae, kilonovae, gamma-ray bursts, but LFBOTs don't quite fit into any of them. Could it be that our entire model of stellar evolution is incomplete? Could there be stars out there that don't follow the usual path of dying in a predictable way? If that's the case, then LFBOTs could be pointing us toward an even bigger discovery, one that changes not just how we understand these bursts, but how we understand the entire life cycle of stars. And this is why astronomers are so eager to catch more of them in real time. Right now, we only have a handful of well-studied LFBOTs. But as new telescopes and observational techniques become available, we may soon be able to detect them more frequently. Some of the upcoming space observatories, like the James Webb Space Telescope and the Vera C. Rubin Observatory, are expected to provide unprecedented insights into these mysterious bursts. The next LFBOT could reveal something completely unexpected, something that forces us to rewrite the textbooks on stellar explosions and high-energy astrophysics. It could show us an entirely new type of object in the universe, one that has been hiding in plain sight all this time. So the question isn't just, what are LFBOTs? It's, what are they trying to tell us about the universe? The answer to that question could reshape our understanding of cosmic events, the life and death of stars, and even the fundamental laws of physics. And the most exciting part? The next big discovery could be just around the corner. The search for luminous fast blue optical transients is still in its infancy, but every new observation brings us closer to unlocking their secrets. Right now, scientists are using powerful observatories like the Hubble Space Telescope, the Very Large Telescope in Chile, and radio telescopes around the world to track these elusive cosmic flashes. But detecting them is only half the battle. The real challenge is figuring out what they mean. One of the biggest roadblocks in understanding LFBOTs is their unpredictability. Unlike supernovae, which are often linked to dying massive stars, LFBOTs seem to appear at random, in locations where we least expect them. Some have been found in the outskirts of galaxies, far away from the dense star-forming regions where most explosions occur. This raises a troubling question. If LFBOTs aren't coming from the usual stellar deaths, then what exactly is producing them? Some researchers have suggested that LFBOTs might be tied to the merger of compact objects, things like neutron stars or black holes colliding with each other. These collisions can release enormous amounts of energy in an instant, potentially explaining why LFBOTs are so bright yet so short-lived. But there's a problem with this idea. When neutron stars or black holes merge, they usually produce gravitational waves, ripples in spacetime that can be detected by instruments like LIGO and Virgo. Yet so far, no LFBOT has been directly linked to a gravitational wave event. This suggests that whatever is causing these bursts might not be a straightforward collision. Another possibility is that LFBOTs come from Magnetars, neutron stars with extremely powerful magnetic fields. Magnetars are known to produce some of the most energetic outbursts in the universe, including gamma-ray flares and fast radio bursts. If a magnetar were to undergo some kind of catastrophic instability, it could, in theory, release a burst of optical light that resembles an LFBOT. But this theory is also incomplete. Magnetars are rare, and most of them are found in dense star-forming regions. If LFBOTs were caused by magnetars, we'd expect to find them in similar environments. Yet, as we've seen, many LFBOTs have appeared in isolated regions of space, far from the places where magnetars usually form. This means we might need to think even further outside the box. Some astrophysicists have proposed that LFBOTs could be the signatures of entirely new types of astrophysical objects, something we haven't even classified yet. Perhaps they are the result of a process we don't fully understand, like the formation of exotic stellar remnants that don't fit into our existing categories. There's even a wild but fascinating idea that LFBOTs could be linked to so-called failed supernovae. Normally, when a massive star reaches the end of its life, it explodes in a brilliant display of light and energy, leaving behind a neutron star or black hole. But in some cases, a star might not explode in the usual way. Instead, it could undergo a partial collapse, where only part of the star is ejected while the core implodes into a black hole. If this happens under the right conditions, it might create an ultra-fast, ultra-bright burst of light, something that could look a lot like an LFBOT. The more we study LFBOTs, the more questions we seem to uncover. Why do some of them fade away quickly while others linger for weeks? Why do they emit such a broad range of wavelengths, from optical light to X-rays? And why are they so rare? If LFBOTs were just another type of stellar explosion, we'd expect to see them much more often. But instead, they appear to be among the rarest and most unusual events in the cosmos. One thing is certain, LFBOTs are forcing astronomers to rethink what we know about the most violent and extreme events in the universe. Every time we detect one, we are peering into a process that defies our expectations. And that's what makes them so exciting. Because in science, the biggest discoveries often come from the things we don't understand. The mystery of LFBOTs is far from solved. But one day, we may look back at these strange flashes as the key to unlocking an entirely new chapter in astrophysics. Until then, we can only watch, wait, and wonder, knowing that the universe still has secrets left to reveal. LFBOTs remind us of how much we still don't know about the universe. For every theory scientists propose, new observations bring unexpected twists, forcing us to reconsider everything. These flashes of blue light defy standard astrophysical models, and every attempt to explain them only seems to add more layers to the mystery. One of the biggest questions is why they appear so suddenly. LFBOTs rise in brightness incredibly fast, sometimes in just a matter of hours. Most stellar explosions take days or even weeks to reach their peak luminosity, but these events defy that norm. They don't just brighten quickly, they also fade just as fast. That kind of behavior suggests an incredibly violent and efficient release of energy. But from what? Let's break down some of the most compelling possibilities. Some astronomers think LFBOTs could be linked to the birth of a black hole. When a massive star collapses, it sometimes forms a black hole instead of exploding in a typical supernova. This process, called a failed supernova, is incredibly difficult to observe because most of the light gets trapped inside the collapsing star. However, if some material manages to escape before it falls in, it could produce a sudden, short-lived burst of intense light, just like an LFBOT. Another theory suggests that LFBOTs could be caused by the explosive death of a Wolf-Rayet star. These are some of the most massive and short-lived stars in the universe, known for their extreme temperatures and powerful stellar winds. If a Wolf-Rayet star were to undergo an unusual form of core collapse, it could generate a rapid, ultra-bright explosion. However, there's a problem with this idea. Wolf-Rayet stars usually exist in dense, star-forming regions, but LFBOTs have been found in isolated locations, where these stars are unlikely to be found. There's also the intriguing possibility that LFBOTs are connected to gamma-ray bursts, GRBs. GRBs are some of the most powerful explosions in the universe, often linked to the deaths of massive stars or the mergers of neutron stars. Some scientists think that LFBOTs could be a special kind of GRB that emits mostly optical light instead of high-energy gamma rays. If that's true, it would mean that LFBOTs represent an entirely new class of transient events, one that we've only just begun to recognize. But perhaps the most exotic theory is that LFBOTs could be caused by an interaction between a black hole and a normal star. In some cases, a black hole can partially consume a star without completely destroying it. This process, known as a partial tidal disruption event, can release bursts of energy as the star's material falls toward the black hole. If an LFBOT is the result of such an event, it could mean that we are witnessing a moment of extreme gravitational interaction, one where a black hole momentarily feeds before the star escapes its grasp. Despite all these theories, no single explanation fully accounts for everything we observe about LFBOTs. They don't fit neatly into any known category of astronomical event, and that's why they're so fascinating. Every time one of these flashes appears, it challenges our understanding of high-energy astrophysics. As astronomers continue to study LFBOTs, new technology will play a crucial role in solving the mystery. Future telescopes, like the Vera C. Rubin Observatory, will be able to scan the sky more frequently and detect these transients in real time. This will help scientists determine how often they occur, where they come from, and what conditions are necessary for them to form. Additionally, space-based observatories like the James Webb Space Telescope might be able to analyze their infrared signatures, giving us new clues about their origins. Ultimately, LFBOTs represent the kind of mystery that drives science forward. They remind us that the universe is far more complex and unpredictable than we ever imagined. Every new discovery about these strange cosmic flashes brings us closer to understanding the extreme processes that shape our universe. Until then, the mystery remains unsolved, one of the many cosmic puzzles waiting for the next breakthrough. LFBOTs are among the most mysterious astronomical events ever observed, and their existence forces us to rethink what we know about stellar explosions, high-energy astrophysics, and even the fundamental processes that govern the universe. These luminous fast blue optical transients defy categorization, appearing unexpectedly in regions of space where no massive stars seem to exist and exhibiting properties that don't fit neatly into any known astrophysical model. The more we study them, the more questions we uncover, and yet, despite all the uncertainty, one thing is clear: LFBOTs are unlike anything we've ever seen before, and their discovery has opened a new frontier in our understanding of the cosmos. One of the most perplexing aspects of LFBOTs is their extreme brightness. They outshine entire galaxies for short periods of time, emitting intense blue light that suggests a temperature of tens of thousands of degrees. This alone is unusual because most stellar explosions tend to cool as they expand, shifting toward redder wavelengths over time. But LFBOTs remain stubbornly blue, suggesting that whatever is powering them is maintaining an extraordinarily high temperature throughout the event. This challenges our current understanding of how energy is distributed in astrophysical explosions. Typically, when a star undergoes a supernova, the outer layers expand rapidly, cooling as they release their energy over days or weeks. However, LFBOTs release an enormous amount of energy in just hours or days, which means that whatever mechanism is driving them must be incredibly efficient at converting mass into light. Another strange feature of LFBOTs is their location. When astronomers first started detecting these events, they expected them to appear in places where massive stars die, dense, active star-forming regions filled with young, massive stars ready to explode in spectacular supernovae. But to their surprise, LFBOTs have been found in the outskirts of galaxies, sometimes in regions where there appear to be no stars at all. This is baffling because it suggests that whatever is producing these events doesn't require the usual conditions associated with stellar deaths. If they aren't coming from dying stars, then what is causing them? This is one of the biggest unsolved questions surrounding LFBOTs, and it has led to a flurry of new theories. One possibility is that LFBOTs are the result of rare types of stellar mergers, cataclysmic collisions between massive objects like neutron stars, black holes, or white dwarfs. When these compact remnants merge, they can produce bursts of energy that temporarily outshine entire galaxies. Some scientists have speculated that LFBOTs might be caused by a newly discovered type of neutron star merger, where one neutron star collides with another, but instead of producing the typical gamma-ray burst, it generates an explosion primarily in optical light. However, there's a major issue with this idea. Neutron star mergers should produce gravitational waves, detectable by observatories like LIGO and Virgo, yet no LFBOT has ever been linked to a recorded gravitational wave event. This suggests that if mergers are responsible for LFBOTs, they must be occurring in a way that doesn't produce strong gravitational waves, or that current detectors are somehow missing them. Another compelling idea is that LFBOTs could be linked to failed supernovae. Normally, when a massive star reaches the end of its life, it explodes in a supernova, leaving behind either a neutron star or a black hole. However, some models predict that in certain cases, the explosion fails, and the star collapses directly into a black hole without producing a traditional supernova. If this happens in just the right way, it might eject a small amount of material at extremely high speeds, generating a short-lived, ultra-bright burst of light, an LFBOT. This would explain why LFBOTs seem to occur in places where no massive stars are currently visible, because the dying stars could have already collapsed into black holes, leaving no trace behind except for the brief burst of light from the failed explosion. However, this theory also has problems, because LFBOTs appear to produce more energy than most failed supernova models predict. There is also speculation that LFBOTs could be linked to Magnetars, neutron stars with incredibly powerful magnetic fields. Magnetars are known to produce some of the most energetic outbursts in the universe, including gamma-ray flares and fast radio bursts. If a Magnetar were to undergo a sudden, catastrophic event, such as a massive magnetic reconnection or a crustal rupture, it could release an enormous amount of energy in a very short period of time. This could theoretically produce the kind of rapid, intense burst of light seen in LFBOTs. However, there's an issue with this idea as well. Magnetars are relatively rare and are typically found in dense star-forming regions, whereas LFBOTs have been observed in isolated locations. If Magnetars are responsible, then either we are missing a major piece of the puzzle about where they form, or LFBOTs require an entirely new type of Magnetar-like object that we haven't yet discovered. Perhaps the most extreme idea is that LFBOTs are the result of exotic new physics, something beyond our current understanding of astrophysics. Some researchers have speculated that they could be signatures of primordial black holes, tiny black holes that may have formed in the early universe and are now evaporating due to Hawking radiation. If these ancient black holes are interacting with normal matter in unexpected ways, they could produce sudden, intense bursts of energy that resemble LFBOTs. Others have suggested that LFBOTs might be linked to unknown particle interactions, new forms of matter, or even the effects of extra dimensions. While these ideas are highly speculative, they highlight just how little we truly know about these mysterious cosmic flashes. Despite all these theories, the true nature of LFBOTs remains elusive. Scientists are racing to gather more data, using the most advanced telescopes available to capture every detail of these fleeting explosions. The Vera C. Rubin Observatory, set to begin operations soon, will be particularly important in this effort, as its powerful survey capabilities will allow astronomers to detect LFBOTs much more frequently and study them in real time. Meanwhile, space-based telescopes like the James Webb Space Telescope and the Hubble Space Telescope are helping to analyze their spectra, providing crucial information about their composition and energy sources. The mystery of LFBOTs is one of the most exciting unsolved puzzles in modern astrophysics. Every time we detect one, we are witnessing a phenomenon that defies explanation, challenging our understanding of how the most extreme events in the universe unfold. Whether they turn out to be a new type of stellar explosion, a sign of unknown physics, or something entirely unexpected, one thing is certain: LFBOTs are rewriting the rules of high-energy astrophysics, and their discovery is just the beginning of a new era of exploration. As we continue to study these enigmatic bursts, we may find answers that lead us to even greater mysteries, proving once again that the universe is far more complex, strange, and wonderful than we ever imagined. The enigma of luminous fast blue optical transients, LFBOTs, continues to perplex astronomers as they analyze more events, yet each discovery only adds to the mystery. These cosmic flashes are among the most energetic, transient phenomena ever observed, but their origins remain uncertain. The challenge lies in their unpredictability and rarity, making them difficult to study in real time. Unlike other well-known astronomical explosions, such as supernovae or gamma-ray bursts, LFBOTs defy traditional classification, appearing suddenly and fading just as quickly. With each new observation, scientists are forced to rethink fundamental assumptions about stellar deaths, black holes, and even the very mechanisms that govern high-energy astrophysical processes. One of the most confounding aspects of LFBOTs is their extreme speed. Typical stellar explosions, such as supernovae, take weeks or even months to reach peak brightness before gradually fading away. In contrast, LFBOTs brighten dramatically within hours, sometimes reaching peak luminosity in just a day. This suggests that whatever process is driving them must release an enormous amount of energy almost instantaneously. The sheer rapidity of these events challenges existing models of stellar collapse and explosion, which generally involve shock waves propagating through layers of gas over longer timescales. If LFBOTs arise from a stellar explosion, it would require a mechanism capable of ejecting vast amounts of material at ultra-high velocities, far beyond what current supernova models predict. Another bizarre feature of LFBOTs is their emission across multiple wavelengths. While their most distinctive characteristic is the intense blue optical light they emit, some LFBOTs have also been detected in X-rays, ultraviolet, and even radio wavelengths. This broad spectrum of emission suggests that LFBOTs involve a complex interplay of extreme physics, possibly including relativistic jets, rapidly expanding shock fronts, and highly magnetized environments. The presence of X-ray and radio signals is particularly intriguing because it implies that there may be a compact object at the heart of these explosions, perhaps a newborn black hole or a rapidly spinning neutron star. If this is the case, LFBOTs could represent a completely new category of astrophysical transient, one that bridges the gap between gamma-ray bursts, supernovae, and Magnetar outbursts. The discovery of the first confirmed LFBOT, at 2018 COW, often referred to simply as the COW, marked a turning point in our understanding of transient events. Located in a relatively quiet region of space, this explosion was unlike anything astronomers had seen before. It was astonishingly bright, incredibly fast, and persisted at high energies for much longer than expected. Follow-up observations revealed strange spectral signatures, hinting at a possible interaction with surrounding material, but the exact nature of the explosion remained elusive. Some researchers suggested that the COW might have been the result of a black hole rapidly consuming the remains of a shredded star, while others proposed that it could have been an unusual type of supernova, where the core collapse of a massive star left behind a rapidly spinning neutron star or magnetar. The lack of a clear answer only deepened the mystery, and subsequent LFBOT detections have done little to simplify the puzzle. Another aspect that makes LFBOTs so puzzling is their unusual locations. Supernovae and gamma-ray bursts tend to occur in well-known star-forming regions, where massive stars are plentiful and eventually undergo explosive deaths. However, LFBOTs often appear in unexpected locations, sometimes in the outskirts of galaxies, or even in regions where no visible stars seem to exist. This raises an important question: if LFBOTs are the explosive deaths of massive stars, why are they occurring in places where massive stars shouldn't be? One possibility is that LFBOT progenitors are older, runaway stars that were ejected from their home galaxies long before they exploded. Another possibility is that they originate from a completely different type of astrophysical system, one that doesn't require massive stars at all. Some astronomers have speculated that LFBOTs could be linked to tidal disruption events, TDEs, where a star wanders too close to a supermassive black hole and gets torn apart by its immense gravitational forces. However, most known TDs occur near the centers of galaxies, where supermassive black holes reside, while LFBOTs are frequently detected far from galactic cores. If LFBOTs are indeed a form of TD, then they would require a different type of black hole, perhaps an intermediate mass black hole lurking in the outskirts of galaxies. Such black holes are thought to be rare, but if they do exist, they could be responsible for some of the most energetic transient events we've ever observed. The role of magnetic fields in LFBOTs is another major question. Some researchers believe that LFBOTs may be powered by Magnetars, which are neutron stars with the most intense magnetic fields known in the universe. When Magnetars undergo sudden magnetic reconnection events, they can release enormous amounts of energy in a very short time. This could potentially explain the rapid brightening of LFBOTs and their multi-wavelength emissions. However, this theory faces the same challenge as other stellar explanations. Magnetars are usually found in young, active star-forming regions, while LFBOTs are often observed in isolated locations. If Magnetars are responsible, then there must be an unknown population of them forming and evolving in ways that we haven't yet understood. The possibility that LFBOTs are entirely new physics remains an open question. Some researchers have suggested that these events could be connected to exotic forms of matter, such as quark stars or strange matter. In some theoretical models, neutron stars under extreme conditions could collapse into objects made entirely of strange quarks, releasing bursts of energy unlike anything we've seen before. If LFBOTs are signatures of such exotic objects, they could provide the first direct evidence for entirely new states of matter. Others have proposed that LFBOTs could be linked to quantum gravitational effects, or even the influence of extra dimensions, although these ideas remain highly speculative. Regardless of their origins, LFBOTs are forcing astronomers to rethink fundamental aspects of high-energy astrophysics. Every new detection provides more clues, yet the mystery only deepens. Future observatories will be crucial in solving this puzzle. The upcoming Vera C. Rubin Observatory, with its ability to scan the sky in unprecedented detail, is expected to detect many more LFBOTs, allowing scientists to gather much-needed statistics on their frequency, distribution, and properties. Space telescopes like James Webb and Hubble will continue to analyze their spectra, looking for chemical signatures that might reveal their composition and formation mechanisms. One of the most exciting prospects is the potential for multimessenger astronomy to provide answers. If LFBOTs are linked to neutron star mergers, black hole formation, or other extreme events, they could produce gravitational waves, neutrinos, or high-energy cosmic rays. Detecting these signals alongside LFBOTs would provide a crucial missing piece of the puzzle, allowing scientists to pinpoint their origins with unprecedented precision. Instruments like LIGO, Virgo, and IceCube are already monitoring the cosmos for such signals, and it may only be a matter of time before we get a definitive answer. For now, the mystery remains. LFBOTs are some of the most extreme and enigmatic explosions in the universe, challenging everything we thought we knew about stellar death, black holes, and high-energy physics. As we continue to unravel their secrets, we may uncover entirely new astrophysical phenomena, perhaps even physics beyond our current theories. One thing is certain: the discovery of LFBOTs is only the beginning of an extraordinary journey into the unknown, and the answers we seek may reshape our understanding of the universe itself. LFBOTs represent one of the biggest challenges in modern astrophysics, primarily because their characteristics refuse to align neatly with any existing cosmic phenomenon. Their brightness, speed, and multi-wavelength emissions defy conventional explanations, forcing astronomers to explore radical ideas that stretch the boundaries of our understanding. Every time a new LFBOT is detected, it raises more questions than answers, leaving researchers scrambling to decipher the cosmic code hidden within these fleeting bursts of energy. Theories range from massive stellar explosions to interactions with dark matter, and even hypothetical physics that could hint at new forces or particles. With so much uncertainty, the study of LFBOTs is more than just a curiosity, it's a potential gateway to revolutionary discoveries. One of the main obstacles in studying LFBOTs is their unpredictability. Unlike supernovae, which are linked to the life cycles of massive stars and occur in somewhat predictable environments, LFBOTs seem to appear at random. They don't follow the same patterns as gamma-ray bursts or tidal disruption events, making it nearly impossible to anticipate their occurrence. This means astronomers must rely on wide-field surveys and rapid-response telescopes to catch them in the act. The Zwicky Transient Facility (CTF) and the All-Sky Automated Survey for Supernovae (ASIS-SN) have played key roles in identifying LFBOTs, but these systems still have limitations. By the time an LFBOT is detected, crucial early-stage data may already be lost, making it difficult to piece together the full sequence of events. One of the strangest aspects of LFBOTs is how they fade. While they initially shine with incredible intensity, their decline doesn't follow the pattern seen in other astrophysical explosions. Supernovae and gamma-ray bursts typically exhibit a gradual fade as their expanding debris interacts with the surrounding environment, but LFBOTs can persist in certain wavelengths for much longer than expected. Some LFBOTs, including the cow, continued emitting X-rays and radio waves for months, hinting at an ongoing energy source rather than a simple explosion. This sustained emission suggests that whatever lies at the heart of an LFBOT isn't just a one-time event. It could be a newly formed compact object, such as a black hole or neutron star, continuously feeding on surrounding material. This raises another intriguing possibility. Could LFBOTs be a form of failed supernova? In some theoretical models, a massive star collapses under its own gravity but doesn't produce a traditional explosion. Instead, the core may instantly form a black hole, swallowing much of the outer material before it can escape. However, if some of the star's mass remains outside the event horizon, it could create a temporary, highly energetic accretion disk that blasts out radiation in all directions. This would explain the rapid onset of brightness, the unusual spectrum of emissions, and the prolonged afterglow in radio and X-ray wavelengths. If this theory is correct, LFBOTs might be offering us a rare glimpse into the birth of black holes in real time, an event that has never been directly observed before. But there's another problem. LFBOTs are far too bright for standard black hole formation models. If they were merely the collapse of a star into a black hole, they shouldn't produce as much visible light as they do. This discrepancy suggests that something else is at play, perhaps an interaction with surrounding material, or a secondary explosion triggered by the collapse itself. Some researchers believe that LFBOTs could be linked to a process called Magneto-rotational explosion, where the collapsing core of a massive star forms a highly magnetized, rapidly spinning neutron star instead of a black hole. The immense magnetic fields generated in this process could drive jets of radiation outward, creating the intense blue light characteristic of LFBOTs. Yet, despite all these theories, no single explanation fully accounts for every observed feature of LFBOTs. Their unusual locations remain one of the biggest puzzles. Why do they appear in places where massive stars shouldn't be dying? If LFBOTs are linked to massive star explosions, we would expect to see them in regions rich in young, hot stars. Instead, they are often found in the outer regions of galaxies, far from active star-forming areas. This suggests one of two things. Either the stars responsible for LFBOTs have been ejected from their home galaxies long before they exploded, or LFBOTs are not caused by the deaths of massive stars at all. Some astronomers have proposed that LFBOTs might be related to interactions between black holes and compact star clusters. In some galaxies, dense groups of stars orbit around central black holes, creating a chaotic environment where stars can be torn apart by gravitational forces. If a black hole disrupts a star in just the right way, it could create a brief, incredibly bright burst of radiation, an event that might look very similar to an LFBOT. However, this theory faces the same issue as other explanations. The locations of LFBOTs don't always match the places where these interactions should be occurring. Another radical idea is that LFBOTs could be powered by exotic forms of matter. Some physicists have speculated that LFBOTs might be linked to quark stars, hypothetical objects where neutrons break down into their constituent quarks, creating an ultra-dense, incredibly energetic state of matter. If a neutron star suddenly transitioned into a quark star, the energy release could be extreme, potentially explaining the brightness and speed of LFBOTs. Others have suggested that LFBOTs could involve strange matter, a theoretical form of matter that could exist under extreme conditions. If a neutron star collapsed into a state of strange matter, the resulting explosion could produce a highly luminous, short-lived burst, perhaps exactly what we see in LFBOTs. There's also the possibility that LFBOTs are revealing something completely unknown, something beyond our current understanding of physics. Some researchers have speculated that they could be linked to quantum gravitational effects or even hidden dimensions of space-time. If the universe has extra dimensions beyond the three we experience, then certain high-energy events could produce radiation that leaks into our observable universe in unexpected ways. While this idea is purely speculative, it highlights just how mysterious LFBOTs truly are. One of the best hopes for solving the mystery of LFBOTs lies in upcoming telescopes and surveys. The Vera C. Rubin Observatory, which is expected to begin operation soon, will provide an unprecedented view of the transient universe. With its ability to scan the entire sky rapidly and detect sudden changes in brightness, it may uncover dozens, or even hundreds, of new LFBOTs, providing astronomers with the statistical data they need to identify patterns and trends. Meanwhile, space-based observatories like the James Webb Space Telescope, JWST, and the future Nancy Grace Roman Space Telescope will help analyze the chemical composition and energy output of these events in unparalleled detail. Another promising avenue is multimessenger astronomy, which looks beyond visible light to detect signals such as gravitational waves, neutrinos, and cosmic rays. If LFBOTs are linked to neutron star mergers or black hole formation, they should produce detectable gravitational waves that instruments like LIGO and Virgo could pick up. Likewise, if LFBOTs involve highly energetic particle acceleration, they might produce bursts of neutrinos that could be detected by facilities like IceCube in Antarctica. The discovery of an LFBOT accompanied by a gravitational wave or neutrino signal would be a game-changer, providing a direct link between these enigmatic flashes and a known astrophysical process. But even if we detect more LFBOTs, will we truly understand them? Their brief, intense nature makes them difficult to analyze, and it's possible that they represent multiple different types of events rather than a single phenomenon. Just as gamma-ray bursts were once thought to be a single class of objects before being divided into short and long types, LFBOTs might eventually be categorized into distinct subgroups, each with its own explanation. Perhaps some LFBOTs are failed supernovae, while others are the result of black holes shredding stars. Some might be linked to quark stars, while others could involve entirely new physics. The challenge will be untangling these possibilities and identifying the true nature of each event. For now, LFBOTs remain one of the most tantalizing mysteries in astronomy. Every new observation brings us closer to understanding them, yet they continue to defy easy explanation. Whether they represent a new type of stellar explosion, a novel form of compact object formation, or even something far more exotic, one thing is certain: LFBOTs are teaching us that the universe is still full of surprises. And as our telescopes and technology improve, we may one day uncover the full story behind these extraordinary cosmic flashes, unlocking secrets that could change our understanding of the cosmos forever. LFBOTs continue to be one of the most baffling transient phenomena ever observed, defying easy classification and forcing astronomers to rethink what they thought they knew about high-energy astrophysical events. Every newly detected LFBOT brings new data, but instead of providing clarity, it often deepens the mystery. The challenge is that these luminous explosions occur unexpectedly, and their rapid fading means that astronomers have only a short window to study them in detail. Unlike supernovae, which can be monitored over weeks, months, or even years, LFBOTs evolve at an astonishing pace, requiring telescopes to react almost immediately. This makes them difficult to capture, and the data collected so far has revealed a strange mix of characteristics that do not align with any known type of explosion, collapse, or merger. One of the most unusual aspects of LFBOTs is their brightness in the optical range, which is much higher than what traditional models predict. The intensity of their light output suggests that they must involve an extraordinary release of energy, but the short timescales indicate that this energy is being generated in a compact region. This is in stark contrast to supernovae, where the brightness results from the expanding outer layers of a massive star slowly cooling and interacting with the surrounding environment. In LFBOTs, the light output appears to be coming from a much more concentrated source, and it fades too quickly to be explained by traditional radioactive decay mechanisms. This rapid decline is a critical clue, as it suggests a highly efficient energy release mechanism that operates on timescales of hours to days, rather than weeks to months. The cow, the first widely recognized LFBOT, demonstrated many of these puzzling properties. It was located in a relatively quiet region of its host galaxy, far from any obvious regions of active star formation. This was immediately strange because most high-energy astrophysical explosions occur in areas rich with young, massive stars. If LFBOTs were related to the deaths of such stars, we would expect to see them in dense star-forming regions. Instead, they appear to be scattered throughout galaxies, often in the outskirts, or in regions without significant recent star formation. This has led to speculation that the progenitors of LFBOTs might not be massive stars at all, but rather compact objects such as neutron stars or black holes interacting with their environments in unexpected ways. One of the leading theories suggests that LFBOTs could be the result of a newborn black hole or neutron star consuming surrounding material in an extremely energetic process. When a star collapses into a black hole, there is a brief window of time where some of the material may remain in a highly energetic, magnetized state before being swallowed completely. This could produce an intense flash of radiation, potentially explaining the extreme brightness of LFBOTs. However, this explanation has its own issues. If LFBOTs were simply the result of newly formed black holes, we would expect to see them more frequently in supernova remnants, which is not always the case. Another possibility is that LFBOTs involve a rare type of binary system, where a compact object like a neutron star or black hole interacts with a companion star in a catastrophic way. One model proposes that LFBOTs occur when a neutron star merges with a helium-rich companion, triggering an explosive outburst as the two bodies collide and disrupt each other. The presence of helium in LFBOT spectra supports this idea, as helium-rich explosions are relatively uncommon in normal supernovae. If this theory is correct, LFBOTs could be providing a unique glimpse into a new class of binary interactions, where extreme gravitational forces cause bursts of energy that outshine entire galaxies for brief moments. However, none of these theories fully explain the multi-wavelength nature of LFBOTs. These events are not just bright and visible light. They also emit high-energy X-rays and sometimes radio waves, which persist much longer than the optical light. The cow, for instance, continued emitting X-rays for months after its initial explosion, suggesting that there was an ongoing energy source long after the visible light had faded. This persistent emission is difficult to reconcile with a simple explosion or stellar collapse, as most high-energy transients fade uniformly across all wavelengths. The prolonged X-ray afterglow hints that something is actively powering the event over an extended period, possibly a rapidly spinning magnetar or an accreting black hole. Magnetars, which are a special type of neutron star with ultra-strong magnetic fields, have been proposed as possible sources of LFBOTs. These objects are known to produce powerful bursts of radiation, and in some cases, they can generate high-energy flares that resemble the properties of LFBOTs. If a magnetar forms in the wake of a stellar explosion, its intense magnetic fields could interact with surrounding material to produce the strange emission signatures observed in LFBOTs. However, while this model explains some aspects of LFBOTs, it does not account for their extreme luminosity or their rapid evolution, leaving open the possibility that something else is at play. One of the biggest challenges in understanding LFBOTs is the lack of a clear pattern in their occurrences. Traditional supernovae follow well-defined relationships based on the type of star that explodes, its environment, and the resulting explosion properties. LFBOTs, on the other hand, do not fit into any of these categories. Some appear in isolated regions of galaxies, while others occur closer to dense stellar clusters. Some show strong helium signatures, while others do not. Some have prolonged X-ray emissions, while others fade almost completely within days. The inconsistency across different LFBOTs suggests that they might not all originate from the same process. Instead, what we currently classify as LFBOTs may actually represent multiple different types of rare astrophysical events that share some common observational characteristics, but have entirely different origins. To truly understand LFBOTs, astronomers will need to catch them even earlier, ideally, within minutes of their initial burst. This will require improvements in sky survey technology and real-time alert systems that can rapidly redirect telescopes to study these fleeting explosions. The upcoming Vera C. Rubin Observatory, with its ability to scan the entire night sky multiple times per night, may be a game-changer in this regard. If astronomers can detect LFBOTs right at the moment they begin, they may be able to capture crucial details that have been missed in previous observations. Another key advancement will come from multimessenger astronomy, which involves detecting cosmic events using more than just light. If LFBOTs are linked to neutron star mergers or black hole formation, they may produce gravitational waves that can be detected by instruments like LIGO and Virgo. Additionally, if they involve particle acceleration, they could generate neutrinos that might be picked up by observatories like IceCube. If an LFBOT is ever detected alongside a gravitational wave or neutrino burst, it would provide a groundbreaking clue about its origins, potentially solving the mystery once and for all. Until then, LFBOTs remain one of the greatest unsolved mysteries of space. They are a reminder that despite all of our technological advancements, the universe is still full of unknowns. Every time we think we have a complete picture of how cosmic explosions work, something like an LFBOT appears and forces us to reconsider everything. Whether they turn out to be the signatures of new kinds of stellar deaths, the birth cries of Magnetars, or something even more exotic, one thing is certain: LFBOTs are not just another astronomical curiosity. They are a window into some of the most extreme physics in the universe, and unlocking their secrets may lead to entirely new discoveries that reshape our understanding of the cosmos. LFBOTs represent the cutting edge of astronomical research, pushing the limits of our observational capabilities and theoretical models. The fact that they do not conform to any known category of astrophysical event suggests that they may be revealing entirely new types of cosmic phenomena. Scientists are now faced with an intriguing possibility. What if LFBOTs are not just extreme versions of known processes, but something completely different? The lack of a clear progenitor, the unusual locations where they appear, and their baffling combination of brightness and rapid decline make them an anomaly in every sense of the word. This is why astronomers are so eager to capture more of them in real time, to gather as much data as possible before these fleeting events vanish into the depths of space. One of the most puzzling aspects of LFBOTs is their color. The term, fast blue optical transient, is not just a random name. It directly refers to their extreme blueness, which indicates incredibly high temperatures. The light from these explosions peaks in the blue part of the spectrum, suggesting temperatures exceeding tens of thousands of degrees. For comparison, typical supernovae can reach similar temperatures, but they do not evolve nearly as fast. The rapid cooling of LFBOTs further complicates matters. Unlike traditional explosions that remain hot for weeks or months, LFBOTs fade within days, implying that whatever process is driving them is incredibly efficient at radiating energy in a short period. This makes it difficult to identify a clear energy source that matches these extreme conditions. One theory gaining traction is that LFBOTs could be linked to failed supernovae, situations where a massive star collapses directly into a black hole without producing a normal explosion. In some cases, it is believed that material falling into the newly formed black hole could generate an intense but short-lived burst of radiation, similar to what we observe in LFBOTs. However, the problem with this idea is that failed supernovae are expected to be extremely dim, as most of the energy is swallowed by the black hole. LFBOTs, on the other hand, are extraordinarily bright, meaning there must be some mechanism allowing energy to escape before being consumed. An alternative possibility is that LFBOTs are connected to relativistic jets, powerful beams of energy that can form when material falls into a black hole at extreme speeds. Some gamma-ray bursts, which are among the most energetic explosions in the universe, are thought to be caused by such jets. If an LFBOT represents a weaker or off-axis version of a gamma-ray burst, it could explain the rapid light curve and high-energy emissions. However, the lack of consistent gamma-ray detections associated with LFBOTs makes this hypothesis uncertain. While some LFBOTs have shown hints of high-energy radiation, it is not always present, which means either the mechanism varies between different events, or an entirely different process is at work. Adding to the confusion is the presence of lingering radio waves in some LFBOTs. The cow, for example, continued emitting radio waves for months after its initial explosion. This suggests that some form of interaction is taking place between the expanding material and the surrounding environment. In supernovae, this type of radio emission is often caused by shock waves plowing into dense gas left behind by the progenitor star. But in LFBOTs, the nature of this interaction remains unclear, as the environment around these explosions does not always seem to contain enough material to produce such strong radio signals. This raises another possibility. What if LFBOTs involve a completely different type of stellar object, such as an intermediate mass black hole? Intermediate mass black holes, IMBHs, are a long-sought class of black holes that are larger than stellar mass black holes but smaller than supermassive black holes. They are thought to exist in dense star clusters and dwarf galaxies, where they may occasionally consume passing stars. If an IMBH were to rip apart a star in a process known as a tidal disruption event, TD, it could theoretically produce an intense but short-lived burst of radiation. Some aspects of LFBOTs resemble TDs, such as their rapid rise in brightness and high-energy emission. However, typical TDs last much longer than LFBOTs, making it unclear whether the same mechanism is at play. If LFBOTs are indeed related to IMBHs, they could provide the first direct evidence of these elusive objects, shedding light on a missing link in black hole evolution. Despite the many theories, one thing is clear: LFBOTs do not fit neatly into any existing category. They may be connected to stellar deaths, neutron-star mergers, black hole formation, or something entirely unknown. Every new observation adds another piece to the puzzle, yet the overall picture remains frustratingly incomplete. The challenge now is to detect more of them as quickly as possible, using a combination of ground-based telescopes, space observatories, and real-time alert systems. The hope is that by studying LFBOTs at multiple wavelengths and comparing their properties, scientists will be able to pinpoint their true origins. Future telescopes such as the James Webb Space Telescope, JWST, and the Vera-C. Rubin Observatory will be instrumental in this effort. JWST's infrared capabilities could help detect any lingering heat signatures from LFBOTs, providing clues about their progenitors. Meanwhile, the Rubin Observatory's ability to scan the sky every few nights will increase the chances of catching LFBOTs in their earliest stages. Additionally, gravitational wave detectors like LIGO may help determine whether LFBOTs are linked to compact object mergers, providing another crucial piece of evidence. If LFBOTs turn out to be a completely new type of astrophysical event, they could revolutionize our understanding of high-energy physics. They may reveal new insights about black hole formation, extreme stellar deaths, or unknown processes that occur in the most extreme environments of the universe. But even if they are eventually explained within existing frameworks, they have already demonstrated how much we still have to learn about the cosmos. The fact that such luminous, energetic, and fast-evolving events have only recently been discovered suggests that there may be many more surprises lurking in the depths of space, waiting to be uncovered. For now, LFBOTs remain one of the biggest mysteries in astrophysics. They challenge our assumptions, defy our models, and remind us that the universe is far more complex than we ever imagined. Each new detection brings excitement, frustration, and the possibility of a breakthrough. As telescopes continue to scan the skies, astronomers eagerly await the next flash of blue light, knowing that within it lies the key to one of the strangest cosmic puzzles ever encountered. The search continues, and with every new LFBOT, we inch closer to an answer, one that may change our understanding of the universe forever. LFBOTs are a perfect example of how the universe keeps surprising us. Just when astronomers think they have a solid understanding of stellar explosions, a completely unexpected type of event comes along and throws all existing models into question. The sheer intensity of LFBOTs, their rapid rise and fall, their extreme temperatures, and their unusual locations all make them a category of their own. And yet, despite being so luminous, They were only discovered recently, raising the question, have they always existed, unnoticed, or are they becoming more frequent due to some unknown cosmic process? One of the key challenges in understanding LFBOTs is their unpredictable nature. Unlike supernovae, which often come from well-understood massive stars at the end of their lives, LFBOTs appear to have no clear progenitor. Astronomers have looked at the regions where LFBOTs occur, hoping to find traces of the kind of massive stars that could explode in such a way, but the search has often come up empty. Many LFBOTs are found in the outskirts of galaxies or even in intergalactic space, where star formation is not very active. This is unusual because most known stellar explosions happen within galaxies, where stars are densely packed. The locations of LFBOTs suggest that either their progenitors are completely different from normal supernovae, or that these objects have somehow been ejected from their home galaxies before exploding. Another aspect that makes LFBOTs so challenging to study is their speed. Most astronomical events take time to unfold. Supernovae can take weeks or months to fade. Neutron star mergers produce long-lasting gravitational waves, and even gamma-ray bursts, while fast, have afterglows that linger. But LFBOTs appear suddenly, brighten incredibly fast, and then fade just as quickly. This means that telescopes need to catch them almost immediately to gather useful data. The first few hours and days after an LFBOT appears are the most critical, as that is when they reveal the most information about their origins. If telescopes miss this window, crucial details are lost, making it much harder to determine what caused the explosion. The extreme brightness of LFBOTs is another piece of the puzzle. They shine up to 100 times brighter than normal supernovae at their peak, despite fading much faster. This means whatever is powering them must release an immense amount of energy in a very short time. One of the leading theories is that LFBOTs involve newly formed black holes or neutron stars surrounded by a dense shell of material. As the explosion occurs, material falling onto the central object could release bursts of energy, creating the intense brightness seen in LFBOTs. However, the problem with this theory is that it still does not fully explain the rapid fading. If a newly formed black hole were responsible, one would expect some kind of prolonged emission from the surrounding material, yet LFBOTs disappear far too quickly. One of the most exciting aspects of studying LFBOTs is the possibility that they could be revealing new physics. Our understanding of astrophysics is based on known physical laws, but LFBOTs might be showing us something beyond what we currently understand. If these explosions involve extreme magnetic fields, exotic states of matter, or unknown particle interactions, they could open the door to entirely new discoveries. Some researchers have even speculated that LFBOTs could be the signature of exotic objects like Quark stars, hypothetical stars made entirely of quark matter, which could form in the aftermath of neutron star collisions. If such objects exist, they could provide crucial insights into the nature of matter at the most extreme densities. Another strange aspect of LFBOTs is their multi-wavelength nature. Unlike many other astrophysical explosions that emit primarily in one part of the spectrum, LFBOTs have been detected across multiple wavelengths, from optical light to X-rays and even radio waves. This suggests that they involve a mix of different physical processes happening at the same time. The radio waves, for example, indicate that LFBOTs are interacting with surrounding material, while the X-rays suggest the presence of extremely hot plasma. But the fact that each LFBOT seems to behave slightly differently makes it difficult to pin down a single explanation. Some show strong X-ray emissions, while others do not. Some emit persistent radio waves, while others fade quickly. This variability suggests that there may be more than one type of LFBOT, or that the conditions surrounding these explosions play a crucial role in shaping their appearance. Despite all these challenges, the search for answers continues. Every new LFBOT provides astronomers with more data, helping to refine existing models and rule out unlikely explanations. Large-scale sky surveys, such as those conducted by the Zwicky Transit Facility and the upcoming Vera C. Rubin Observatory, are expected to play a crucial role in discovering more LFBOTs. These observatories scan the sky regularly, capturing thousands of new transient events every night. By comparing the properties of different LFBOTs, researchers hope to find patterns that could reveal their true nature. One of the biggest questions surrounding LFBOTs is whether they are a new type of stellar death, or something else entirely. If they are related to supernovae, they could represent a previously unknown way in which stars die, perhaps a type of explosion that only occurs under very specific conditions. If they are linked to black holes, they could provide new insights into how black holes form and grow. And if they are something completely different, they could be pointing toward entirely new astrophysical processes that we have yet to understand. The discovery of LFBOTs is a reminder of how much we still do not know about the universe. Even with advanced telescopes and decades of research, new cosmic mysteries continue to emerge, challenging our understanding of physics and forcing us to reconsider what we thought we knew. In a way, LFBOTs represent the frontier of modern astrophysics, an enigma that refuses to be easily classified, defying expectations and hinting at deeper mysteries waiting to be uncovered. As astronomers continue to search for answers, one thing is certain: LFBOTs will not be the last mystery the universe throws our way. They are just one piece of a much larger puzzle, a glimpse into the unknown forces shaping the cosmos. The next LFBOT could be detected at any moment, and with it, new clues may emerge. Will it finally reveal the true nature of these strange explosions, or will it deepen the mystery even further? Only time will tell. But one thing is for sure: whatever LFBOTs are, they are a sign that the universe is far more complex, strange, and fascinating than we ever imagined. The fact that LFBOTs remain so elusive, despite their extreme brightness, suggests that they are either incredibly rare or that they have been happening all along but escaping detection due to their fleeting nature. Unlike supernovae, which can linger for weeks or even months, LFBOTs shine intensely for only a few days before rapidly fading away. This means that if astronomers are not actively scanning the sky at the right time, an LFBOT can come and go without leaving much of a trace. But now that we know they exist, the big question is, what exactly causes them? Theories range from the plausible to the wildly speculative. Some researchers believe that LFBOTs could be the result of a failed supernova, an explosion where a massive star begins to collapse into a black hole but, instead of triggering a typical supernova, it experiences a more unusual event. In this scenario, a massive star might lose most of its outer layers before its core collapses, leaving behind only a small amount of material to explode in an ultra-bright but short-lived event. This could explain why LFBOTs are so luminous yet fade quickly. They simply do not have as much material to sustain a longer explosion. Another theory suggests that LFBOTs might be linked to binary star systems where a dense object, such as a neutron star or black hole, is stripping material away from a companion star. If the material builds up in just the right way, it could trigger an explosive outburst, creating the signature rapid rise and fall of an LFBOT. This might also explain why LFBOTs sometimes appear in unexpected locations, as binary systems can be ejected from their host galaxies due to gravitational interactions. Yet another possibility is that LFBOTs could be caused by the merger of two compact objects, such as a neutron star colliding with a white dwarf. When two such objects spiral inward and collide, they release an enormous amount of energy, potentially creating the kind of brief but intense explosion that characterizes LFBOTs. This idea is particularly interesting because it suggests that LFBOTs could be a missing link between known cosmic phenomena, perhaps related to kilonovae, the explosions that occur when two neutron stars merge. One of the biggest clues about LFBOTs comes from their unusual spectra. When astronomers analyze the light from an LFBOT, they find evidence of incredibly high temperatures, often exceeding 30,000 Kelvin, much hotter than typical supernovae. This intense heat suggests that whatever is happening in an LFBOT is more extreme than a normal stellar explosion. Some researchers speculate that LFBOTs might involve Magnetars, neutron stars with ultra-powerful magnetic fields. If a Magnetar forms in the aftermath of a massive explosion, its intense magnetic fields could interact with surrounding material, generating bursts of radiation that match what we see in LFBOTs. But what if LFBOTs are something even stranger? Some astronomers have considered the possibility that they could be related to dark matter, one of the biggest mysteries in physics. Dark matter is an invisible substance that makes up most of the mass in the universe, yet it does not emit or interact with light in the way normal matter does. If certain types of exotic dark matter particles can interact with regular matter under extreme conditions, they might trigger explosive events like LFBOTs. While this idea remains highly speculative, it is not entirely out of the question. After all, the universe has repeatedly shown that it holds surprises beyond what we currently understand. One of the most exciting aspects of LFBOT research is that new detections could happen at any time. Telescopes like the Vera C. Rubin Observatory, set to begin operations soon, will scan the sky with unprecedented detail, making it more likely that we will catch LFBOTs in their earliest stages. If astronomers can observe an LFBOT within minutes or hours of its appearance, they might be able to gather crucial evidence that sheds light on its origins. Future space telescopes, especially those capable of detecting high-energy radiation, could provide even more insight by capturing X-ray or gamma-ray emissions from LFBOTs, revealing details that are currently hidden. But until then, the mystery remains. Every time an LFBOT is detected, it raises more questions than answers. What is their true nature? Are they connected to known astrophysical processes, or are they something entirely new? Could they be the first evidence of an unknown type of cosmic explosion? As astronomers continue their search, one thing is certain: LFBOTs are yet another reminder that the universe is far more mysterious than we ever imagined. And as our technology advances, we may finally uncover the truth behind these extraordinary cosmic flashes. LFBOTs challenge everything we think we know about how stars live and die. Traditionally, the life cycle of a massive star follows a somewhat predictable pattern. It burns through its fuel, fuses heavier elements, and eventually meets its end in a supernova or collapses into a black hole or neutron star. But LFBOTs suggest that something else is happening, something much faster and far more energetic than what we expect from a typical stellar death. If they do come from dying stars, then they might represent an entirely new way for a star to explode, one that defies our current models. This is why every new observation of an LFBOT is so critical. Each one has the potential to reshape our understanding of stellar evolution. One of the strangest things about LFBOTs is their unpredictability. Unlike other cosmic explosions, which tend to occur in well-understood locations, such as within galaxies with active star formation, LFBOTs often appear in places where they simply should not exist. Some have been found far outside the main regions of galaxies, in intergalactic space, where there are no obvious sources for such powerful explosions. This alone makes them incredibly difficult to explain. If LFBOTs were just a new type of supernova, we would expect them to follow the same rules as other stellar explosions. But they don't. Instead, they seem to pop up in random locations, making it harder to pin down a single cause. This unusual placement suggests that whatever causes LFBOTs might involve objects that are either ejected from galaxies or exist in ways we do not yet understand. One possibility is that LFBOTs are tied to stars that have been flung away from their home galaxies due to gravitational interactions. When two massive galaxies collide, they can create extreme gravitational forces that send some stars hurtling into intergalactic space at incredible speeds. If one of these runaway stars were to reach the end of its life, it could explode in an LFBOT-like event. But this theory raises more questions than it answers. For one, why would these explosions be so different from typical supernovae? And why do they produce so much light in such a short period of time? Another strange feature of LFBOTs is their extreme luminosity. They are among the brightest transient events in the universe, outshining even the most powerful supernovae for a brief moment. To produce this much energy, something incredibly violent must be happening. One of the leading theories is that LFBOTs involve the rapid collapse of a massive object into a black hole or neutron star, generating an enormous burst of energy in the process. This could explain their brightness but does not fully account for their rapid fading. Unlike typical supernovae, which can remain visible for weeks or months, LFBOTs vanish almost as quickly as they appear. Some scientists have suggested that LFBOTs could be the result of an exotic form of stellar destruction, such as the collision of two ultra-dense objects like neutron stars. When neutron stars merge, they release an immense amount of energy, often producing gamma-ray bursts and gravitational waves. But LFBOTs do not seem to match the typical pattern of these events. Instead, they exhibit unique spectral signatures that set them apart from any known cosmic explosion. This suggests that while LFBOTs might share some similarities with known astrophysical phenomena, they are fundamentally different in ways we do not yet understand. One particularly interesting idea is that LFBOTs could be the result of a failed supernova. Normally, when a massive star reaches the end of its life, it undergoes a core collapse supernova, where the outer layers are ejected while the core collapses into a neutron star or black hole. But in some cases, the explosion may be incomplete, leading to a much more rapid and energetic event. If LFBOTs are failed supernovae, they could represent an entirely new class of stellar deaths, one that challenges our understanding of how stars end their lives. What makes LFBOTs even more mysterious is the fact that they emit radiation across multiple wavelengths, including optical, ultraviolet, and sometimes even X-rays. This suggests that they involve incredibly high-energy processes that go beyond what we typically see in stellar explosions. Some researchers believe that the presence of X-rays could indicate the involvement of a rapidly spinning neutron star or magnetar, an object with an extremely powerful magnetic field. If LFBOTs are linked to magnetars, they could provide valuable insights into how these exotic objects form and evolve. Another possibility is that LFBOTs are linked to black holes in a way we do not yet understand. Some theories suggest that they could be the result of a black hole consuming a star in a highly unusual way. Normally, when a black hole pulls a material from a surrounding star, it produces a long-lasting glow known as an accretion disk. But if the process were to happen in an extremely violent and rapid manner, it might create a brief, intense flash of light before fading away, similar to what we see in LFBOTs. There is also speculation that LFBOTs could be connected to the deaths of ultramassive stars that exist on the fringes of known stellar physics. Some of the largest stars in the universe are so massive that they defy conventional models of stellar evolution. These stars may undergo exotic forms of collapse that produce explosions unlike anything we have ever seen. If LFBOTs are tied to these rare stellar giants, they could provide a glimpse into the final moments of some of the most extreme objects in the cosmos. One of the most fascinating aspects of LFBOT research is the possibility that they could be completely new phenomena, something we have never encountered before. Throughout history, astronomy has been filled with moments where scientists discovered unexpected cosmic events that reshaped our understanding of the universe. From gamma-ray bursts to fast radio bursts, many of the most exciting discoveries in astrophysics have come from detecting strange signals that did not fit into existing models. LFBOTs could be yet another example of this, a brand new type of cosmic explosion that challenges everything we thought we knew about the life cycles of stars. As astronomers continue to study LFBOTs, new observations could help unlock their secrets. Upcoming telescopes, such as the Vera C. Rubin Observatory, are designed to scan the sky for transient events, making it more likely that we will catch LFBOTs in their earliest stages. If we can observe them within minutes or hours of their appearance, we might be able to gather crucial data that sheds light on their origins. Future space telescopes, especially those capable of detecting high-energy radiation, could provide even more insight by capturing X-ray or gamma-ray emissions from LFBOTs, revealing details that are currently hidden. For now, though, the mystery remains unsolved. Every time an LFBOT is detected, it raises more questions than answers. What is their true nature? Are they connected to known astrophysical processes, or are they something entirely new? Could they be the first evidence of an unknown type of cosmic explosion? As astronomers continue their search, one thing is certain: LFBOTs are yet another reminder that the universe is far more mysterious than we ever imagined. And as our technology advances, we may finally uncover the truth behind these extraordinary cosmic flashes. LFBOTs are unlike anything we've ever encountered, and that alone makes them one of the most exciting mysteries in modern astrophysics. But the key to understanding them lies in gathering more data, tracking every instance of these bizarre explosions, measuring their spectra, analyzing their locations, and determining what, if anything, they have in common. Right now, we are in the early stages of studying these events, much like how astronomers were baffled by gamma-ray bursts when they were first detected. It took decades to figure out their origins, and it may take just as long, if not longer, to truly grasp what LFBOTs are and what they mean for our understanding of the universe. One of the biggest challenges in studying LFBOTs is how short-lived they are. Unlike supernovae, which can remain visible for weeks or even months, LFBOTs fade away in a matter of days. This makes them incredibly difficult to capture in real time. By the time telescopes are redirected to study one, it may already be too late to observe the critical early moments that could reveal crucial details about the explosion's nature. The best way to study them is through wide-field survey telescopes that scan large portions of the sky continuously, increasing the chances of catching these events as they happen. This is where future observatories will play a critical role. The Vera C. Rubin Observatory, set to begin operations soon, will be one of the best tools for finding and studying LFBOTs. It will use an advanced camera system to take rapid, repeated images of the sky, allowing astronomers to detect sudden changes in brightness across vast cosmic distances. If an LFBOT appears, it can be identified almost immediately, giving scientists a better chance to study it in detail before it fades away. Other telescopes, like the James Webb Space Telescope, could provide valuable follow-up observations in the infrared, allowing researchers to examine how these explosions interact with their environments. One of the strangest aspects of LFBOTs is their apparent randomness. Unlike most cosmic explosions, which tend to occur in regions of active star formation, LFBOTs seem to appear in all sorts of unexpected locations, including the outskirts of galaxies and even deep in intergalactic space. This suggests that whatever is causing them does not follow the typical rules of stellar evolution. If LFBOTs were simply a rare type of supernova, we would expect to find them in the same places where massive stars are found. But instead, they seem to break this pattern entirely, hinting at an origin that we do not yet understand. One possibility is that LFBOTs are the result of interactions between black holes and rogue stars, stars that have been flung out of their home galaxies and are traveling alone through space. If a rogue star were to get too close to an intermediate mass black hole, the immense gravitational forces could rip it apart in a process known as a tidal disruption event. But LFBOTs do not match the characteristics of typical tidal disruptions, suggesting that if black holes are involved, something very unusual is happening. Another intriguing theory is that LFBOTs might be linked to an entirely new type of astrophysical object, something we have never seen before. Throughout history, astronomy has repeatedly uncovered new classes of cosmic phenomena that defy existing models. Fast radio bursts, FRBs, for example, were once a complete mystery, and even today, we do not fully understand their origins. LFBOTs might be another example of this, a phenomenon that does not fit neatly into our current understanding of how the universe works. If that is the case, then studying LFBOTs could lead to one of the biggest discoveries in modern astrophysics. One particularly bold hypothesis is that LFBOTs could be the signature of something even more exotic, such as the formation of a quark star. Quark stars are theoretical objects that could form when a neutron star is compressed to such an extreme degree that its neutrons break down into a sea of free quarks. If such an event were to occur suddenly, it might produce an extremely bright but short-lived burst of light, exactly what we see in LFBOTs. If this theory turns out to be correct, it would mean that LFBOTs are providing the first observational evidence for an entirely new state of matter in the universe. Another possibility is that LFBOTs are linked to Magnetars, neutron stars with the most powerful magnetic fields in the universe. Magnetars are already known to produce extreme bursts of energy, and some scientists believe that LFBOTs could be a new type of Magnetar-powered explosion. If this turns out to be the case, then studying LFBOTs could help us understand the role of Magnetars in the universe, as well as the conditions under which they form. Whatever their true nature, LFBOTs are forcing astronomers to rethink some of the most fundamental aspects of stellar evolution and cosmic explosions. They do not fit neatly into any known category, which means that our current theories are missing something important. This is what makes LFBOTs so exciting. Every new discovery related to them has the potential to rewrite our understanding of the cosmos. As our technology improves, we will inevitably learn more about LFBOTs and what causes them. Upcoming space telescopes, such as the European Space Agency's Athena X-ray Observatory, could provide crucial insights by detecting high-energy emissions from these events. If we can pinpoint their exact locations, analyze their spectra in detail, and determine whether they are associated with known objects like black holes or neutron stars, we might finally unlock their secrets. But until then, LFBOTs remain one of the most puzzling and fascinating mysteries in modern astrophysics, one that continues to challenge everything we think we know about how the universe works. The mystery of LFBOTs is a reminder of how much we still don't understand about the universe. Every time we think we have a solid grasp of how cosmic phenomena work, something like LFBOTs appears and forces us to reconsider our assumptions. This is the beauty of astrophysics. It is an ever-evolving field, where new discoveries constantly push the boundaries of our knowledge. If history is any indication, the solution to the LFBOT puzzle may lead to an even deeper mystery, one that reshapes our understanding of stellar explosions, exotic objects, or perhaps even the fundamental forces of the universe itself. One of the key factors that make LFBOTs so unusual is their immense brightness. They can be up to 100 times more luminous than a normal supernova, yet they fade away at an incredibly rapid pace. Normally, when a star explodes, the energy release follows a predictable pattern based on the radioactive decay of elements like nickel-56. But LFBOTs do not follow this pattern at all. They brighten and fade far too quickly, suggesting a completely different energy source is at play. Some scientists suspect that LFBOTs might be powered by the rapid formation of a compact object, such as a black hole or a neutron star, surrounded by an accretion disk that emits an intense burst of energy before collapsing into darkness. If this is the case, LFBOTs could represent a missing link in our understanding of how these extreme objects form. Another strange aspect of LFBOTs is their spectral composition. When astronomers study light from cosmic events, they look at the spectrum, the breakdown of light into different wavelengths, to determine what elements are present. In typical supernovae, we see clear signatures of elements like hydrogen, helium, oxygen, and iron. But in LFBOTs, the spectral lines appear highly unusual, sometimes featuring elements we wouldn't expect to see in such large amounts. This suggests that whatever is causing LFBOTs is not just a normal star reaching the end of its life but something far more exotic. One idea that has been gaining traction is that LFBOTs could be the explosive deaths of Wolf-Rayet stars. These are massive, evolved stars that have shed their outer layers, leaving behind a hot, dense core. If a Wolf-Rayet star were to undergo a sudden core collapse, it could produce an extremely bright but short-lived explosion, much like what we see in LFBOTs. However, this theory doesn't explain why LFBOTs are appearing in unexpected locations, far from star-forming regions. If they were just a rare type of stellar death, we would expect to see them in the same places as other supernovae, but instead, they seem to be scattered across the universe in a way that doesn't make sense. Some researchers have speculated that LFBOTs might be linked to failed supernovae. In some cases, when a massive star collapses, it doesn't produce a typical explosion, but instead directly forms a black hole, with most of the energy disappearing into the event horizon. However, if some of that energy were released in a burst before the collapse was complete, it might look like an LFBOT, an intense but fleeting flash of light, followed by nothing. If this hypothesis is correct, studying LFBOTs could give us our first real glimpse into the process of black hole formation in real time. Another theory suggests that LFBOTs could be the result of binary star mergers. When two stars orbit each other closely, they can eventually spiral inward and collide, producing a massive release of energy. If one of the stars is a neutron star, the collision could create an intense burst of light, much like an LFBOT. This idea is supported by the fact that some LFBOTs have been observed near known neutron star systems. However, the timescales and energy levels involved don't quite match what we would expect from a typical merger event, meaning there are still many unanswered questions. What makes LFBOTs so difficult to explain is that they do not fit neatly into any existing category of cosmic explosions. They are too fast and too bright to be ordinary supernovae, but they also lack the defining features of gamma-ray bursts or other known transient events. This has led some scientists to propose that LFBOTs might represent an entirely new type of astrophysical phenomenon, something that has never been observed before. If this turns out to be true, it would mean that the universe is even stranger and more complex than we ever imagined. One of the biggest challenges in solving the mystery of LFBOTs is the lack of observational data. Because these events are so rare and short-lived, astronomers have only been able to study a handful of them in detail. The first confirmed LFBOT, at 2018 CAL, was discovered in 2018, and since then, only a few more have been detected. To truly understand what is causing these explosions, scientists need more data, more observations, more spectra, and more follow-up studies. Fortunately, with the next generation of telescopes coming online, we may soon have the tools to crack this mystery wide open. Future space telescopes, like the Nancy Grace Roman Space Telescope, will be able to scan the sky for transient events with unprecedented sensitivity. Ground-based observatories, like the Extremely Large Telescope, ELT, currently under construction in Chile, will provide high-resolution spectra that could reveal the chemical makeup of LFBOTs in exquisite detail. By combining these observations with data from radio telescopes and gravitational wave detectors, astronomers hope to piece together a complete picture of what is happening in these mysterious explosions. Some researchers have even proposed that LFBOTs could be related to exotic new physics. For example, if dark matter particles were capable of interacting in ways we don't yet understand, they could potentially produce explosive bursts of energy under the right conditions. While this is still a highly speculative idea, it underscores the fact that LFBOTs are challenging our current understanding of how the universe works. If they turn out to be linked to some previously unknown physical process, they could open the door to entirely new areas of research. One of the most exciting aspects of studying LFBOTs is the potential for unexpected discoveries. Throughout history, some of the biggest breakthroughs in science have come from investigating strange anomalies that didn't fit existing theories. The discovery of pulsars, for example, completely changed our understanding of neutron stars. The detection of the first fast radio bursts, FRBs, led to an entirely new field of research. LFBOTs might be another one of these game-changing discoveries, something that forces us to rewrite the textbooks on stellar evolution, black hole formation, or even the fundamental laws of physics. As we continue to study LFBOTs, one thing is clear: these events are telling us something important about the universe, and we need to pay attention. Whether they turn out to be a new class of supernova, the signatures of black hole formation, or something even more exotic, they are a reminder that the cosmos is still full of surprises. The more we learn about LFBOTs, the more we realize how much we still don't know, and that is what makes them one of the most exciting mysteries in modern astrophysics. LFBOTs continue to defy our understanding, and each new observation only deepens the mystery. One of the most puzzling aspects is how rapidly they appear and disappear. Traditional supernovae take weeks to reach peak brightness and can linger for months, slowly fading as their radioactive material decays. But LFBOTs behave nothing like that. They reach their peak within days and then fade in just a couple of weeks. The sheer speed of this process suggests an incredibly powerful mechanism at work, one that must generate an immense amount of energy in an incredibly short time. To put this into perspective, the energy output of an LFBOT in just a few days can rival the total energy output of our Sun over its entire lifetime. That means whatever is causing these explosions is capable of releasing unimaginable amounts of energy almost instantly. The most common supernovae we see are the result of a massive star collapsing under its own gravity. But if LFBOTs are something different, it raises a fundamental question: what kind of cosmic event could possibly unleash such an extreme burst of energy so quickly? Some scientists speculate that LFBOTs could be related to Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. When a magnetar forms, its intense magnetic field can twist and tangle, building up enormous amounts of energy. If this energy is suddenly released, it could produce a blindingly bright explosion. But while magnetars can release powerful flares, they don't typically match the exact behavior of LFBOTs. The timescales and energy distributions don't line up perfectly, meaning that even if magnetars are involved, they can't be the whole story. Another possibility is that LFBOTs could be linked to black holes consuming material in an unusually extreme way. Normally, when a black hole pulls in gas and dust, the material forms an accretion disk that heats up and emits energy over time. But what if, instead of a slow process, something caused a massive influx of material to be swallowed all at once. This kind of rapid accretion event could theoretically produce a brief but intense burst of light. However, it still doesn't fully explain why LFBOTs appear in such unexpected locations, far from the dense stellar environments where black holes are usually found feeding on matter. Perhaps one of the most exotic theories is that LFBOTs could be the signature of a completely new type of astrophysical event, something we've never seen before. Some researchers have proposed that they might be evidence of strange quark stars, hypothetical objects made of an exotic form of matter where normal protons and neutrons are broken down into a soup of fundamental particles. If such a star were to collapse, it could potentially release a vast amount of energy in a very short time, much like what we see in LFBOTs. But since no direct evidence of quark stars has ever been found, this remains purely speculative. Even more outlandish is the idea that LFBOTs could be linked to cosmic strings, hypothetical defects in spacetime left over from the early universe. If a cosmic string were to interact with a black hole or a neutron star, it might trigger a sudden and dramatic energy release. While there is no concrete evidence for cosmic strings, they are theoretically possible within certain models of physics. If LFBOTs turned out to be connected to such exotic structures, it could revolutionize our understanding of the universe's fundamental nature. One of the biggest challenges in studying LFBOTs is simply catching them in time. Since they appear and fade so quickly, astronomers need to act fast when one is detected. The best way to do this is through automated sky surveys, telescopes that scan the entire sky on a regular basis, looking for changes. Some of the most important tools in this effort include the Zwicky Transient Facility, CTF, and the Vera C. Rubin Observatory, which is expected to come online soon and could provide crucial insights into these enigmatic explosions. But even when an LFBOT is detected, figuring out its origins requires follow-up observations across multiple wavelengths. Optical telescopes can see the bright flashes, but radio and X-ray telescopes provide additional clues about what's happening behind the scenes. Some LFBOTs have been observed to emit powerful X-ray and radio signals long after the initial explosion fades, hinting that they might be leaving behind compact remnants, possibly neutron stars or black holes. If we can study these afterglows in more detail, they might hold the key to unlocking the mystery. One particularly intriguing case is at 2022 TSD, an LFBOT discovered in 2022 that exhibited unusual properties compared to previous detections. This event was located in a region of space where no known star formation was occurring, adding to the confusion about where these explosions originate. The data from at 2022 TSD suggested that whatever caused the explosion was different from ordinary stellar deaths, reinforcing the idea that LFBOTs might represent a completely new type of astrophysical event. Ultimately, solving the LFBOT mystery will require a combination of better observations, theoretical modeling, and perhaps even entirely new physics. These events challenge some of our most fundamental assumptions about how stars die, how black holes form, and how energy is released in extreme cosmic environments. The fact that they don't fit into any known category suggests that something truly unexpected is happening, and that makes them one of the most exciting puzzles in modern astronomy. What's even more fascinating is the possibility that LFBOTs could be just the tip of the iceberg. If they represent a new class of transient events, there could be other, even rarer explosions out there waiting to be discovered. The universe is full of surprises, and as our observational technology improves, we are likely to uncover more phenomena that defy explanation. LFBOTs remind us that, despite all we have learned, we are still just beginning to understand the vast and mysterious cosmos that surrounds us. The deeper we dive into the enigma of luminous fast blue optical transients, LFBOTs, the more it becomes clear that these cosmic bursts defy our traditional categories of stellar events. They are too fast to be supernovae, too bright to be ordinary stellar flares, and too erratic to fit neatly into the known processes of black hole or neutron star activity. Their unpredictability forces astronomers to rethink not only what causes these explosions but also whether they might be linked to something entirely new in astrophysics. One of the major reasons LFBOTs are so difficult to explain is that they occur in places where we don't expect such violent activity. Most supernovae, for instance, take place in galaxies with active star formation, where massive stars live and die in explosive events. But LFBOTs often appear in galactic outskirts, or in regions with little stellar activity. This alone suggests that whatever is causing them isn't following the same rules as traditional supernovae. Another puzzle lies in their color and luminosity. LFBOTs shine with an intensely blue light, indicating that they are incredibly hot, much hotter than typical stellar explosions. This suggests a rapid, high-energy process that generates extreme temperatures almost instantly. Traditional supernovae take time to reach their peak heat, but LFBOTs flare up almost immediately. Their fast rise time and brief duration make them an outlier among known cosmic explosions, hinting at a fundamentally different physical mechanism at play. Some astronomers have proposed that LFBOTs might be a special type of core collapse event in a massive star. When a massive star reaches the end of its life, its core collapses under gravity, sometimes forming a black hole or neutron star in the process. In a typical supernova, the outer layers of the star are blasted away in an explosion that radiates light for months. But what if, instead of a traditional supernova, something caused the collapse to release energy in an entirely different way? One theory suggests that if a rapidly rotating star collapses asymmetrically, it could trigger a powerful but brief jet of energy, leading to an explosion that mimics an LFBOT. This jet model is particularly intriguing because it aligns with the idea that LFBOTs might be related to gamma-ray bursts, GRBs, some of the most energetic events in the universe. GRBs are believed to occur when massive stars collapse and form black holes, producing relativistic jets that emit intense bursts of gamma rays. However, GRBs are typically associated with very distant galaxies and have distinct radiation signatures that don't fully match those of LFBOTs. If LFBOTs are indeed some variation of this process, they may represent a new type of stellar death that has gone undetected until now. Yet another possibility is that LFBOTs originate from interactions between compact objects, such as neutron stars or black holes, and their surroundings. If a neutron star were to merge with another dense object in a binary system, the resulting collision could generate a short-lived but highly energetic outburst. This would explain the brevity and intensity of LFBOTs while also accounting for their erratic locations in space. However, binary mergers are usually accompanied by gravitational wave signals, and so far, no direct gravitational wave detections have been linked to an LFBOT event. The extreme brightness of LFBOTs also raises another question: could these events be related to supermassive black holes at the centers of galaxies? Normally, when a star strays too close to a black hole, it gets torn apart in what's known as a tidal disruption event, TD. These events can produce bursts of light, but they don't match the speed and intensity of LFBOTs. However, some researchers speculate that if a small, dense object, like a neutron star, were to be torn apart by an intermediate mass black hole, it could create a unique type of explosion that might resemble an LFBOT. Despite all these theories, the reality is that none of them fully explain the nature of LFBOTs. Every new event that is observed seems to add another layer of complexity rather than bringing us closer to a definitive answer. The challenge lies not only in detecting these events but in capturing enough data to determine their true nature. Because they fade so quickly, astronomers need to act within days, or even hours, of their discovery to gather the necessary observations. This is where modern technology and large-scale surveys become crucial. The Zwicky Transient Facility (ZTF) has played a major role in detecting LFBOTs, as it scans the sky multiple times per night, allowing researchers to catch these fleeting events. The upcoming Vera C. Rubin Observatory will take this capability even further, promising to detect more transient phenomena than ever before. By tracking LFBOTs across multiple wavelengths, from optical light to X-rays and radio waves, scientists hope to build a more complete picture of what's happening during these explosions. Interestingly, some of the most valuable data on LFBOTs has come from space-based telescopes like NASA's Swift Observatory, which specializes in detecting high-energy transient events. Swift's ability to rapidly pivot toward new sources of X-rays and gamma rays has allowed researchers to study LFBOTs in greater detail than ever before. One of the key findings is that some LFBOTs exhibit delayed X-ray flares long after the optical light has faded, suggesting that whatever caused the explosion may still be interacting with its environment in complex ways. One particularly strange case is at 2018 Cal, the first well-documented LFBOT, which became known simply as the Cal. This explosion was unlike anything seen before. It was 10 to 100 times brighter than a typical supernova, but it faded at an incredibly rapid pace. Its spectrum revealed unusual signatures, including high-energy X-ray emissions that persisted for weeks. The Cal remains one of the best-studied LFBOTs, but even with all the data collected, its origins remain uncertain. It could have been the birth of a black hole, a failed supernova, or something entirely new. The mystery of LFBOTs isn't just about understanding one type of explosion, it's about uncovering new physics that might reshape how we think about the universe. If LFBOTs are linked to previously unknown stellar deaths, they could help us refine our understanding of how stars evolve and die. If they are connected to exotic objects like Magnetars or Quark stars, they could provide the first real evidence for these elusive phenomena. And if they turn out to be something completely new, they could open the door to a whole new branch of astrophysics. For now, astronomers continue to scan the skies, hoping to catch the next LFBOT in action. Each new detection brings a fresh opportunity to gather data, test theories, and perhaps, finally, uncover the truth behind these bizarre cosmic flashes. The universe has always been full of surprises, and LFBOTs remind us that there are still many cosmic secrets waiting to be unraveled. The mystery of LFBOTs goes beyond just their brightness, speed, and location. It extends into the very physics that govern the most extreme environments in the universe. If these events are caused by something we've never seen before, then they could reveal new insights into how matter behaves under unimaginable conditions. The fact that LFBOTs produce an unusually strong presence of high-energy X-rays and radio waves suggests that they might be powered by an ultra-compact object, like a newly formed black hole or an exotic neutron star. But even if that's the case, we still don't fully understand how these explosions happen, why they are so brief, or why they seem to occur in unusual places. One of the strangest aspects of LFBOTs is their rapid decline in brightness. Most explosive events in space, like supernovae, tend to follow predictable patterns. They brighten over several days or weeks, peak in intensity, and then fade slowly over the course of months. But LFBOTs defy this behavior entirely. They reach their peak brightness in just a day or two and then fade within a matter of weeks. This means whatever process is generating their immense energy is shutting down much faster than any known explosion. This rapid fade-out suggests that the energy source behind them is either incredibly efficient at releasing its power in a short time, or is being smothered by its own environment just as quickly as it ignites. Astronomers have considered whether LFBOTs could be a completely new kind of stellar collapse, perhaps related to failed supernovae. In some cases, a massive star might start to explode but fail to fully eject its outer layers, causing most of the explosion's energy to be absorbed or funneled into a rapidly forming black hole. This process could create a short-lived but incredibly bright burst of energy, matching the characteristics of LFBOTs. However, most failed supernovae are expected to occur in dense, star-forming regions, whereas LFBOTs are often detected in unexpected locations. Another idea suggests that LFBOTs could be linked to Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Magnetars are known for their extreme energy bursts, which sometimes appear in X-rays or gamma rays. If an LFBOT represents the birth of a Magnetar under extreme conditions, it could explain the intense energy output and rapid fading. The challenge with this theory is that it doesn't fully explain why LFBOTs have such an unusual color spectrum, or why they don't seem to leave behind the same kind of remnants seen in other Magnetar-related explosions. Some astronomers have even proposed that LFBOTs could be tied to exotic physics, such as the collapse of an object made of quark matter or the interaction between dark matter and normal matter. If an LFBOT represents the sudden conversion of a neutron star into something even denser, such as a quark star, it might release an immense amount of energy in a very short time. This would explain their rapid rise and fall, as well as their strange emission patterns. However, quark stars remain theoretical, and there is little direct evidence to support this idea. though LFBOTs might provide a clue that such exotic objects actually exist. One of the most pressing questions about LFBOTs is whether they are related to fast radio bursts, FRBs, another mysterious type of cosmic event. FRBs are brief but powerful pulses of radio waves that last only milliseconds but release as much energy as the sun does in an entire year. While FRBs and LFBOTs occur on vastly different timescales, some researchers have speculated that they could be connected. If LFBOTs involve highly magnetized neutron stars, they might produce FRBs under certain conditions. This would mean that LFBOTs are part of a broader family of transient phenomena that we are only beginning to understand. Another possibility is that LFBOTs are the result of extreme accretion events, where matter is suddenly dumped onto a compact object like a black hole or neutron star, triggering a brief but powerful outburst of energy. If a neutron star were to suddenly gain a large amount of material from a companion star or an accretion disk, it could generate an explosion similar to an LFBOT. However, this theory doesn't fully explain the rapid fade-out of these events, or their unusual colors, meaning that if accretion is involved, it must be happening in a way that we've never observed before. The unusual environments in which LFBOTs are found may offer an important clue. Unlike most known stellar explosions, which occur in the densely populated arms of galaxies where new stars are forming, LFBOTs often appear in the outer regions of galaxies or even in intergalactic space. This suggests that whatever is causing them isn't dependent on the presence of large, young stars. Some scientists have considered whether LFBOTs could be linked to old, dying stellar remnants that have been flung into these locations due to gravitational interactions. If, for example, a neutron star were ejected from a galaxy and later collided with another object in deep space, it might produce an explosion similar to an LFBOT. What makes this mystery even more frustrating is that despite detecting several LFBOTs over the years, astronomers still don't have enough data to confirm any one theory. Part of the challenge is that these events are rare and unpredictable, meaning that telescope surveys must constantly scan the sky in hopes of catching one in real time. Additionally, because LFBOTs evolve so quickly, researchers need to act fast to collect data before they fade away. In many cases, by the time follow-up observations are conducted, the event has already dimmed too much to study in detail. However, the next generation of observatories promises to revolutionize our ability to study these fleeting cosmic outbursts. The Vera C. Rubin Observatory, which is set to begin full operation soon, will scan the entire night sky every few days, allowing it to detect transient events like LFBOTs with unprecedented accuracy. Meanwhile, the James Webb Space Telescope, JWST, and upcoming X-ray observatories will provide deeper insights into the high-energy physics behind these events. Ultimately, solving the mystery of LFBOTs may require a combination of different observational techniques, theoretical models, and perhaps even entirely new physics. They might be the missing link between different types of stellar deaths, a clue to exotic forms of matter, or something we haven't even imagined yet. The fact that they don't fit into any existing category of cosmic explosion makes them one of the most intriguing open questions in modern astrophysics. As astronomers continue to piece together the puzzle, each new detection brings us one step closer to understanding what's really happening in these cosmic fireballs. Whether LFBOTs turn out to be a strange type of supernova, a new form of black hole birth, or something entirely unexpected, they remind us that the universe is still full of surprises. In the coming years, with more advanced telescopes and better observational strategies, we may finally uncover the true nature of these bizarre and brilliant flashes of light in the depths of space. LFBOTs continue to challenge our understanding of stellar evolution, black hole formation, and the extreme physics of high-energy cosmic events. Despite their rarity, each detection provides more data that can be used to refine our theories, but the more we learn, the stranger these phenomena become. Every time astronomers think they are close to pinning down a definitive explanation, new observations raise even more questions. One of the most perplexing issues is the sheer diversity of LFBOT events. While they share common characteristics, no two are exactly alike, suggesting multiple potential origins or a completely unknown underlying mechanism. A key mystery surrounding LFBOTs is their immense energy output, which cannot be easily explained by conventional astrophysical models. Supernovae, for instance, follow well-understood principles. A massive star runs out of nuclear fuel, its core collapses under gravity, and the resulting explosion sends its outer layers hurtling into space. But LFBOTs appear to release their energy in an entirely different way. Their peak luminosity can be up to 100 times brighter than typical supernovae, and they do so in a fraction of the time. This extreme energy release suggests that they are powered by an incredibly efficient mechanism, potentially involving newly formed black holes, highly magnetized neutron stars, or even processes we have yet to discover. One promising line of research involves looking at LFBOTs in other wavelengths beyond visible light. So far, studies have shown that these transients emit in X-rays and radio waves, but the patterns of this radiation are still puzzling. Unlike typical supernovae, which show a steady decline in all wavelengths over time, LFBOTs sometimes display unexpected flares in the X-ray spectrum even after their optical light has faded. This suggests that something is still actively generating energy long after the initial explosion. One possibility is that LFBOTs leave behind a rapidly spinning neutron star or black hole that continues to interact with its surroundings, producing delayed bursts of radiation. Some scientists have proposed that LFBOTs could be related to a phenomenon known as a fallback supernova. In this scenario, when a massive star collapses, some of its outer layers fail to escape the gravitational pull of the newly formed neutron star or black hole. Instead, this material falls back onto the compact object, triggering a secondary explosion or prolonged energy release. This could explain the unusual brightness and fast evolution of LFBOTs, as well as their strange locations, if they originate from isolated massive stars that have been ejected from their home galaxies. They could appear in unexpected places. Another intriguing hypothesis is that LFBOTs might be related to mergers of compact objects, such as neutron-star collisions or neutron-star black hole mergers. These events are known to produce powerful bursts of energy, such as gamma-ray bursts, grbs, and kilonovae, but LFBOTs seem to differ in significant ways. Unlike grbs, which last only seconds to minutes, LFBOTs persist for days or weeks before fading. And unlike kilonovae, which produce a distinctive infrared glow due to the radioactive decay of heavy elements, LFBOTs appear much bluer in color. This means that while mergers remain a possibility, they would have to occur under conditions we have never observed before. One particularly fascinating aspect of LFBOTs is their potential connection to exotic physics. If they are powered by the formation of quark stars, hypothetical objects even denser than neutron stars, this could provide a rare glimpse into the behavior of matter under extreme conditions. In neutron stars, atoms are crushed so tightly that protons and electrons combine to form neutrons. But some theories suggest that if the pressure is high enough, even neutrons break down into a soup of fundamental particles called quarks. A transition from a neutron star to a quark star could release an immense amount of energy in a very short time, potentially explaining the rapid rise and fall of LFBOTs. However, quark stars remain purely theoretical, and no direct evidence of their existence has been found. Some researchers have even suggested that LFBOTs could be linked to the interaction of normal matter with dark matter. Dark matter makes up about 85% of the universe's mass, yet it remains invisible and mysterious, only detectable through its gravitational effects. If an LFBOT were caused by a neutron star or black hole interacting with a dense clump of dark matter, it could trigger an energy release unlike anything we have seen before. This would open an entirely new avenue of research, potentially helping to solve one of the biggest mysteries in modern physics. To truly understand LFBOTs, astronomers need more data, but capturing these fleeting events is extremely difficult. Because they appear unpredictably and fade quickly, telescopes must constantly scan the sky to catch them in real time. Large-scale surveys, such as the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will play a crucial role in identifying more LFBOTs and studying their evolution from start to finish. Meanwhile, follow-up observations with space-based telescopes like the James Webb Space Telescope, JWST, and high-energy observatories like the Chandra X-ray Observatory will provide deeper insights into their physical properties. If LFBOTs are indeed a new type of stellar explosion, They could revolutionize our understanding of how stars die and how compact objects form. If they are linked to exotic matter or dark matter interactions, they could provide clues about the fundamental nature of the universe. Either way, solving the mystery of LFBOTs will require a combination of cutting-edge observational techniques, innovative theoretical models, and perhaps even new physics that we have yet to discover. For now, LFBOTs remain one of the most tantalizing enigmas in astrophysics, a cosmic puzzle waiting to be solved. With each new detection, astronomers get closer to unraveling the truth behind these strange, luminous explosions. As our telescopes grow more powerful and our ability to study transient events improves, we may soon find the answers we seek, or uncover even deeper mysteries that challenge everything we thought we knew about the universe. The search for answers about luminous fast blue optical transients, LFBOTs, continues to push the boundaries of what we understand about the universe. Every new detection adds another piece to the puzzle, yet the mystery only deepens. These cosmic events defy traditional explanations, displaying characteristics that don't quite fit into any known astrophysical category. They are too fast to be typical supernovae, too bright to be ordinary stellar flares, and too erratic to be neatly categorized alongside gamma-ray bursts or kilonovae. Scientists are left with more questions than answers, and as more telescopes scan the sky, the hope is that new observations will provide the missing links needed to finally explain what LFBOTs truly are. One of the most perplexing aspects of LFBOTs is their unpredictable nature. They do not appear in any obvious pattern, nor do they seem to originate from any specific type of galaxy or environment. Unlike supernovae, which are typically associated with massive stars and star-forming regions, LFBOTs have been found in locations where stellar explosions would not normally be expected. Some have even been detected far outside their host galaxies, in the seemingly empty void of intergalactic space. This raises several intriguing possibilities. Could these explosions be the remnants of rogue stars that were ejected from their home galaxies before they exploded? Or are they caused by entirely new astrophysical processes that do not require the presence of a host galaxy at all? One theory that has gained traction is that LFBOTs could be linked to stellar mass black holes interacting with their environments in unexpected ways. If a black hole were to suddenly accrete a large amount of matter in a short time, it could trigger an outburst of energy resembling an LFBOT. However, this theory comes with its own challenges. Black holes are known for their ability to generate powerful bursts of radiation when consuming matter, but their typical emissions do not match the rapid rise and fall of an LFBOT's brightness. If black holes are involved, they must be accreting matter in a completely different way than what we've observed before. Another possibility is that LFBOTs could be the signatures of newly formed Magnetars, highly magnetized neutron stars that emerge from certain types of stellar collapses. Magnetars are known to produce some of the most extreme bursts of energy in the universe, including soft gamma repeaters and fast radio bursts. If an LFBOT were the result of a Magnetar being born, the intense magnetic fields could be responsible for the rapid and intense bursts of energy observed. However, this hypothesis does not explain why LFBOTs are so much brighter than known Magnetar-related events. It's possible that we are seeing an entirely new class of Magnetar, one with properties that have never been observed before. The role of exotic physics in LFBOTs is another intriguing avenue of research. Some scientists have speculated that these transients could be linked to dark matter interactions, strange quark stars, or even the collision of exotic objects that have yet to be discovered. If LFBOTs are powered by unknown physics, they could provide a rare glimpse into processes that challenge our fundamental understanding of the universe. The idea that we could be witnessing a completely new form of energy release is both exciting and daunting, as it suggests there are still fundamental forces in the cosmos that we have yet to comprehend. As more LFBOTs are detected, astronomers are refining their search methods and developing new techniques to capture these fleeting events in greater detail. Large-scale sky surveys, like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will be instrumental in identifying more LFBOTs and tracking their evolution in real time. Meanwhile, space-based telescopes such as the James Webb Space Telescope, JWST, and high-energy observatories like the Chandra X-ray Observatory will allow scientists to study their properties in greater depth. These observations may eventually lead to a breakthrough, revealing whether LFBOTs represent an entirely new class of astrophysical phenomenon, or a previously unseen variation of known cosmic events. Until then, LFBOTs remain one of the most tantalizing unsolved mysteries in astrophysics. They challenge everything we think we know about how stars evolve, how matter interacts under extreme conditions, and how the universe generates some of its most powerful explosions. With each new discovery, the boundaries of our knowledge are pushed further, and the possibility of uncovering something truly groundbreaking grows ever more likely. The universe is vast, mysterious, and full of surprises, and LFBOTs are a stark reminder that we are only just beginning to scratch the surface of its deepest secrets. Luminous fast blue optical transients LFBOTs are a stark reminder that the universe is far more chaotic and unpredictable than we ever imagined. With each new discovery, we are forced to question the very foundation of our astrophysical models. Scientists have spent decades classifying different types of stellar explosions, supernovae, kilonovae, gamma-ray bursts, but LFBOTs refuse to fit into any of these neat categories. Their rapid rise, extreme brightness, and sudden disappearance break the conventional rules of astrophysics, forcing researchers to rethink what might be possible in the universe. Every known model of stellar evolution and explosive phenomena struggles to explain the sheer intensity of these events, leaving us with more questions than answers. One of the biggest mysteries surrounding LFBOTs is the sheer speed at which they unfold. Unlike traditional supernovae, which take weeks to peak in brightness, LFBOTs explode to their maximum luminosity in just hours. This rapid energy release suggests that whatever is causing these events must be incredibly powerful, perhaps an unknown type of stellar death, an unprecedented interaction between cosmic bodies, or even an entirely new physical process that has never been observed before. The speed of these explosions suggests an incredibly compact source, possibly involving neutron stars, black holes, or magnetars. But the problem is that none of the known mechanisms involving these objects produce the exact characteristics of an LFBOT. Something new, something beyond our current understanding, is at play. What makes this even stranger is that LFBOTs are not just fast, they are also extremely bright. They shine with a luminosity up to 100 times that of a typical supernova, yet they vanish far too quickly for their brightness to be explained by any known type of stellar collapse. If a massive star were undergoing a traditional explosion, its expanding outer layers would continue glowing for weeks or even months. But LFBOTs fade much too quickly, suggesting that whatever is fueling them burns out in a matter of days. This has led some scientists to propose that LFBOTs might not be the result of an exploding star at all, but rather something much more exotic. One theory is that LFBOTs could be caused by black holes shredding stars in a process known as a tidal disruption event, TD. When a star ventures too close to a black hole, the intense gravitational forces rip it apart, sending its material into a violent accretion disk that glows brightly before being swallowed. However, traditional TDs do not match the extreme speed and brightness of LFBOTs, meaning that if black holes are involved, they must be consuming matter in a way that we have never seen before. Some scientists speculate that LFBOTs could be a unique type of TD, one that involves an intermediate mass black hole, an elusive class of black holes that exist between stellar mass and supermassive black holes. If such black holes exist, they could be responsible for creating the extreme bursts of energy seen in LFBOTs, but direct evidence for this is still lacking. Another possibility is that LFBOTs could be linked to exotic neutron-star collisions. Neutron stars are some of the densest objects in the universe, and when they collide, they can produce some of the most extreme explosions ever observed. Kilonovae, which are produced when two neutron stars merge, have been studied in detail thanks to gravitational wave detections. However, LFBOTs differ from kilonovae in several key ways, particularly in their speed and brightness. This has led some to wonder if LFBOTs could be a new type of neutron-star interaction, perhaps the result of a highly magnetized neutron star colliding with another dense object in a way that generates an unprecedented burst of energy. Even more speculative ideas suggest that LFBOTs could be related to new physics. Some researchers have proposed that they could be linked to dark matter interactions, strange quark stars, or even completely unknown subatomic processes. If this is true, then studying LFBOTs could open a window into physics beyond the standard model, potentially revealing forces or particles that have never been detected before. The fact that LFBOTs do not behave like any other known astronomical event means that they could be our first glimpse into an entirely new realm of physics, one that could revolutionize our understanding of the universe. Despite their mystery, LFBOTs are becoming increasingly detectable thanks to advancements in astronomical surveys. Telescopes like the Zwicky Transient Facility, CTF, and upcoming observatories like the Vera C. Rubin Observatory are scanning the sky at an unprecedented rate, allowing astronomers to catch these events in real time. This is crucial because LFBOTs happen so quickly that any delay in observation could mean missing out on vital clues about their origins. By detecting them earlier and studying their evolution in detail, scientists hope to finally unravel the processes that drive these enigmatic explosions. In the coming years, multi-wavelength observations will be key to solving the LFBOT puzzle. While they are primarily detected in optical light, astronomers are now using X-ray, radio, and ultraviolet telescopes to gather additional data. Each wavelength reveals different aspects of the explosion, providing a more complete picture of what is happening. For example, if LFBOTs produce strong X-ray emissions, this could indicate the presence of an accreting black hole or neutron star. If they emit radio waves, it could suggest that they are blasting material into space at near-light speeds, similar to gamma-ray bursts. Every new piece of data brings us closer to understanding these cosmic enigmas, but so far, no single explanation has been able to fully account for all of their strange properties. LFBOTs serve as a reminder that the universe is still full of surprises. Even with all of our advancements in technology and scientific understanding, nature continues to throw us curveballs. The fact that these explosions defy classification suggests that we still have much to learn about how extreme astrophysical events work. Whether they turn out to be the result of unusual stellar deaths, exotic compact objects, or entirely new physical processes, one thing is certain: LFBOTs represent one of the greatest unsolved mysteries in modern astronomy. The search for answers will continue, with astronomers around the world keeping a close watch on the sky in the hopes of catching the next LFBOT in action. With each new detection, the puzzle becomes more complex, but also more exciting. Perhaps the next LFBOT will provide the final clue needed to unlock the mystery, or perhaps it will reveal even more unexpected properties that challenge our understanding even further. Either way, LFBOTs are proving to be one of the most intriguing discoveries of our time, and whatever their true nature may be, they are bound to teach us something new about the universe. LFBOTs are more than just a curiosity. They could be a gateway to understanding some of the most extreme and unexplored physics in the universe. Every time one of these events is detected, it forces astronomers to reconsider what they thought they knew about cosmic explosions, compact objects, and the high-energy processes that shape the cosmos. What makes LFBOTs so perplexing is that they seem to share characteristics with multiple known astronomical phenomena, while simultaneously breaking the rules of all of them. Their rapid rise in brightness mirrors gamma-ray bursts, but their optical nature and lingering glow are more reminiscent of supernovae. Yet they do not fit neatly into either category, suggesting that we might be dealing with an entirely new class of astrophysical events, one that challenges the very framework of our understanding. One of the key questions surrounding LFBOTs is their energy source. Traditional supernovae are powered by nuclear fusion and the collapse of a massive star's core, while gamma-ray bursts are believed to be powered by the formation of black holes and the subsequent release of relativistic jets. But LFBOTs exhibit behaviors that do not match either of these processes. The sheer amount of energy they release in such a short time frame suggests that they must involve some form of extreme energy conversion, perhaps an interaction between magnetic fields, matter, and radiation that has never been observed before. Some researchers have proposed that LFBOTs could be powered by Magnetars, neutron stars with the most intense magnetic fields in the universe. If a Magnetar were to undergo a violent instability or a sudden energy release, it might produce the kind of intense, short-lived explosion seen in LFBOTs. But even this theory struggles to explain the specific light curves and wavelengths detected in these events, leaving scientists searching for better answers. Another crucial mystery is why LFBOTs seem to appear in unexpected locations. Traditional supernovae occur in galaxies rich with star formation, where massive stars live out their short lives before exploding. But some LFBOTs have been detected in intergalactic space, far from any known star-forming region. This raises an intriguing question. If LFBOTs are the result of stellar deaths, how did the progenitor stars end up so far from their home galaxies? One possibility is that they were ejected from their original locations due to gravitational interactions, possibly involving supermassive black holes or other extreme astrophysical processes. Another possibility is that LFBOTs are not tied to normal stellar evolution at all, but rather to some other kind of cataclysmic event that can occur in the void between galaxies. Observing LFBOTs across multiple wavelengths has revealed even more perplexing details. Some LFBOTs have been detected emitting strong X-ray and radio signals long after their initial explosion, suggesting that they are producing powerful shockwaves that continue interacting with their environment. This is unusual because traditional supernovae tend to fade more predictably, with their light diminishing over time as their expanding remnants cool. The prolonged emissions from LFBOTs hint at some kind of ongoing energy input, possibly from an unseen compact object like a neutron star or a black hole continuing to inject energy into the system. This opens the possibility that LFBOTs might be connected to objects we have yet to fully understand, such as Quark stars or other hypothetical exotic matter configurations that could produce unpredictable bursts of energy. The speed at which LFBOTs rise and fall also has significant implications for astrophysics. The light from these events must be coming from an extremely compact region, otherwise, the rapid changes in brightness would not be possible. This suggests that whatever is powering these explosions is operating on an incredibly small scale, perhaps just a few hundred kilometers across. For comparison, a typical supernova's expanding shell of debris covers millions of kilometers. This extreme compactness could indicate that LFBOTs originate from the very densest objects in the universe, such as merging neutron stars, rapidly collapsing stellar remnants, or even highly magnetized white dwarfs undergoing explosive transformation. Some theories even suggest that LFBOTs could be linked to exotic quantum processes. If extreme magnetic fields or high-energy particle interactions are involved, it is possible that these explosions are producing conditions that momentarily alter the laws of physics as we know them. There is speculation that LFBOTs might be linked to strange matter, an exotic state of matter that could form under extreme conditions and release enormous amounts of energy in the process. If true, this would mean that LFBOTs are not just unusual explosions, but possibly the first observational evidence of a previously unknown form of matter. Another possibility is that LFBOTs are connected to black holes in ways we have yet to comprehend. Some astrophysicists speculate that these events could be the result of black hole mergers that produce unexpected bursts of electromagnetic radiation. While traditional black hole mergers are primarily detected through gravitational waves, it is conceivable that under certain conditions, they could also produce intense optical flashes similar to those seen in LFBOTs. This would make LFBOTs one of the most intriguing forms of electromagnetic counterparts to black hole mergers, something that could drastically enhance our ability to study these enigmatic objects. The unpredictability of LFBOTs makes them particularly challenging to study. Since they appear without warning and disappear so quickly, astronomers have to rely on fast-response telescopes to capture their properties before they fade. Instruments like the Swift Observatory, which can rapidly shift its focus to new transient events, have played a crucial role in tracking these explosions. Upcoming space telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, may provide even more detailed observations that could finally reveal the true nature of LFBOTs. In the long run, solving the mystery of LFBOTs could have profound implications for our understanding of the universe. If they turn out to be a new type of supernova, they could provide insights into the final moments of massive stars and the conditions under which they explode. If they are related to compact object mergers, they could help bridge the gap between electromagnetic and gravitational wave astronomy, offering a new way to study the most extreme objects in existence. And if they are linked to unknown physics, They could revolutionize our understanding of fundamental forces and particles, potentially leading to breakthroughs in both astrophysics and quantum mechanics. As astronomers continue to study LFBOTs, each new detection adds another piece to the puzzle. The more we learn about these strange explosions, the closer we get to understanding their origins. But with each new discovery, new questions arise. Are LFBOTs a single phenomenon, or are they a collection of different types of rare astrophysical events that share similar characteristics? Do they originate from isolated stellar remnants, or are they the result of interactions between cosmic objects we have yet to fully understand? And most importantly, what do they tell us about the hidden forces at work in the universe? The search for answers continues, and with every new observation, we move closer to uncovering the truth. But until we fully understand LFBOTs, they will remain one of the greatest cosmic mysteries of our time, an enigma that defies explanation and challenges everything we thought we knew about the nature of stellar explosions. LFBOTs represent one of the biggest challenges in modern astrophysics. Unlike other transient events, which generally fit into well-understood categories like supernovae, gamma-ray bursts, or tidal disruption events, LFBOTs refuse to be neatly classified. This forces astronomers to consider more unconventional explanations, including entirely new astrophysical mechanisms that have yet to be discovered. Each time one of these events is detected, it provides a rare and fleeting glimpse into an extreme process that is likely occurring all across the universe, but has largely remained hidden from our view. These events are not just scientific curiosities. They could fundamentally reshape our understanding of high-energy astrophysics, the evolution of massive stars, and even the basic laws of physics that govern the cosmos. One of the most striking features of LFBOTs is their immense brightness. These explosions can outshine entire galaxies for brief periods, releasing an extraordinary amount of energy in a matter of days. To put this into perspective, the energy output of an LFBOT can be equivalent to the combined light of billions of stars, concentrated into a single explosive event. This kind of power suggests that the process behind LFBOTs is tapping into a source of energy far more extreme than typical stellar explosions. Some researchers believe that this might involve exotic forms of matter, like quark gluon plasma, which is theorized to exist in the densest cores of neutron stars. If LFBOTs are producing such states of matter, they could provide a unique window into physics that has, until now, only been explored in particle accelerators like the Large Hadron Collider. The rapid rise time of LFBOTs is another confounding mystery. Traditional supernovae take weeks or even months to reach their peak brightness as the explosion propagates outward and the ejected material interacts with surrounding gas. LFBOTs, however, brighten within days or even hours, suggesting that the explosion originates from an extremely compact region. This implies that the object responsible is much smaller than a typical supernova progenitor star. Some astronomers speculate that LFBOTs could be linked to the deaths of stars in binary systems, where interactions with a companion star might accelerate the explosion and cause it to unfold in an unusual way. Others suggest that these events could be the signature of an entirely new type of stellar collapse, one that does not conform to the standard models of black hole or neutron star formation. Adding to the confusion is the fact that LFBOTs seem to produce high-energy radiation, including X-rays and gamma rays, long after the initial explosion. This suggests that whatever is powering them does not simply disappear after the blast, but instead continues to interact with its surroundings in a violent and energetic way. One possibility is that these events leave behind highly magnetized neutron stars, known as Magnetars, which can continue injecting energy into the explosion for extended periods. If true, LFBOTs could represent a missing link between supernovae and some of the most extreme objects in the universe. Another possibility is that the explosion itself is just the first phase of a more complex process, where material falling back onto a central compact object, like a newly formed black hole, fuels additional bursts of radiation over time. Perhaps one of the most intriguing aspects of LFBOTs is their apparent ability to defy location-based expectations. The first LFBOT ever detected, at 2018 Cal, occurred in an unexpected region of space, and subsequent events have also been found in places where scientists would not typically expect such high-energy explosions to occur. This raises fundamental questions about what kinds of objects can produce LFBOTs and where they originate. If LFBOTs are tied to stellar deaths, why do they sometimes appear in regions with little star formation? One potential answer is that the objects responsible for LFBOTs have been ejected from their home galaxies due to gravitational interactions, perhaps involving supermassive black holes. Another possibility is that LFBOTs are linked to an entirely different type of astrophysical process, one that does not require a traditional stellar evolution pathway. The sheer unpredictability of LFBOTs makes them difficult to study, but it also makes them incredibly exciting. Unlike many other astronomical phenomena that follow well-defined rules and patterns, LFBOTs seem to break every rule. They are fast, powerful, and seemingly rare, yet they might actually be more common than we realize, hidden in the vastness of space, waiting to be detected by the next generation of telescopes. As technology improves and astronomers develop more sophisticated ways to search for these fleeting bursts of energy, it is likely that we will uncover even more examples of LFBOTs, potentially revealing new variations that challenge our current theories even further. There is also the possibility that LFBOTs could be connected to something even more mysterious, phenomena that exist outside of our current understanding of physics. Some researchers have speculated that these events could involve interactions between dark matter and ordinary matter, producing exotic forms of radiation that we have never seen before. Others have suggested that LFBOTs might be the result of unknown quantum processes taking place in extreme astrophysical environments. While these ideas remain speculative, the fact that LFBOTs do not fit neatly into any known category means that we cannot rule out the possibility that they are revealing something truly revolutionary. In recent years, astronomers have begun to detect more LFBOT-like events, each adding new layers of complexity to the mystery. Some of these explosions have shown unexpected color variations, suggesting that they may be composed of unusual elements, or involve previously unseen physical processes. Others have displayed strange afterglows that fade in unpredictable ways, hinting at ongoing interactions with surrounding material. These observations are helping scientists refine their models, but they also raise new questions about what mechanisms could be responsible for such unusual behavior. Ultimately, solving the puzzle of LFBOTs will require a combination of observational breakthroughs and theoretical advances. Astronomers will need to collect more data from future detections, using both ground-based and space-based observatories to capture every possible detail. At the same time, physicists will need to explore new models of high-energy astrophysical processes, considering possibilities that may have previously seemed too extreme or unlikely. As our understanding of the universe grows, LFBOTs may turn out to be a key piece of the puzzle, providing insights that could reshape our knowledge of stellar evolution, black hole formation, and even the fundamental laws of physics themselves. Despite all the unanswered questions, one thing is clear: LFBOTs represent one of the most exciting frontiers in modern astronomy. Each new detection brings us one step closer to unraveling their true nature, and with upcoming missions designed to study transient events in greater detail, we may soon have the answers we seek. But until then, these luminous fast blue optical transients will remain one of the greatest mysteries in the cosmos, brief, brilliant, and utterly baffling. LFBOTs have captured the attention of astronomers because they challenge our understanding of how high-energy astrophysical events unfold. These luminous explosions defy expectations in nearly every way, rising and fading at unprecedented speeds, emitting a strange combination of optical, X-ray, and radio signals, and appearing in unexpected locations. Each new observation adds more complexity to the puzzle, forcing researchers to rethink existing models of stellar evolution, black hole formation, and even the fundamental properties of matter under extreme conditions. One of the most pressing questions is whether LFBOTs represent an entirely new class of astrophysical events, or if they are an extreme variation of already known phenomena. Traditional supernovae follow a predictable sequence. When a massive star reaches the end of its life, its core collapses under the force of gravity, triggering an explosion that rips through the outer layers of the star and leaves behind a neutron star or black hole. This process takes time, with the explosion's brightness peaking over weeks or months. LFBOTs, however, brighten in just a few days, suggesting that the underlying mechanism is operating on an entirely different timescale. This rapid evolution implies that whatever is powering these events must be far more compact and energetic than a typical supernova progenitor. One potential explanation involves black holes consuming material in an unusual way. When matter falls into a black hole, it usually forms an accretion disk, a swirling structure of gas and dust that heats up and emits radiation as it spirals toward the event horizon. In some cases, this process can generate powerful bursts of energy, like the ones seen in tidal disruption events, where a star gets torn apart by a supermassive black hole. However, LFBOTs do not seem to match the characteristics of tidal disruption events, leading some researchers to propose that they might involve black holes interacting with dense stellar remnants, possibly neutron stars that have collapsed in an unexpected manner. Another intriguing possibility is that LFBOTs are linked to the birth of Magnetars, ultra-magnetized neutron stars that form under extreme conditions. Magnetars are known for their violent bursts of energy, often producing high-energy flares that can outshine an entire galaxy. If LFBOTs are connected to Magnetar formation, it could explain their rapid rise time and unusual afterglows. The extreme magnetic fields of these objects could be channeling energy into the explosion in ways that have never been observed before, creating a new type of astrophysical event that bridges the gap between supernovae and other high-energy transients. Adding to the mystery, LFBOTs exhibit strange behavior in the radio spectrum, emitting prolonged bursts of radio waves long after the initial explosion has faded. This suggests that they are interacting with surrounding material in an unusual way, possibly producing powerful shockwaves that continue to generate energy long after the initial event. Some astronomers believe that this radio emission could be the result of a relativistic jet, a stream of particles moving at nearly the speed of light. If LFBOTs do indeed produce relativistic jets, it would make them similar to gamma-ray bursts, but with important differences in their timing and brightness. This has led some researchers to consider whether LFBOTs might be a missing link between different types of high-energy explosions, revealing new pathways for how energy is released in the most extreme environments in the universe. The location of LFBOTs is another clue that something unusual is happening. Most high-energy transients are found in specific regions of galaxies. Supernovae tend to appear in areas of active star formation, while gamma-ray bursts are often linked to the deaths of massive stars. However, LFBOTs do not seem to follow this pattern. They have been observed in unexpected locations, sometimes in the outskirts of galaxies or even in regions where few stars are present. This suggests that whatever is producing these events is either highly mobile, perhaps a population of rogue stellar remnants moving through space, or that the explosions themselves are being triggered by an unknown mechanism that does not rely on traditional stellar evolution pathways. The sheer unpredictability of LFBOTs makes them difficult to study, but it also makes them one of the most exciting mysteries in modern astronomy. Each new detection provides another piece of the puzzle, but instead of bringing clarity, it often raises even more questions. What kind of astrophysical engine could produce such powerful bursts of energy in such a short amount of time? Are LFBOTs a completely new type of explosion, or are they an extreme variation of something we have already observed? Could they be linked to exotic physics that has never been seen before? One of the most fascinating aspects of LFBOTs is that they may not be as rare as they initially seemed. Early detections suggested that these events were incredibly uncommon, but as astronomers refine their search methods, more LFBOTs are being discovered. This raises the possibility that LFBOTs are actually a significant part of the universe's high-energy landscape, but they have remained hidden from view because of their fleeting nature. Future telescopes, equipped with better instruments for detecting transient events, may reveal that LFBOTs are happening all around us, providing a new perspective on the most violent processes in the cosmos. As technology advances, astronomers are developing new strategies to catch LFBOTs in action. Space-based observatories like the James Webb Space Telescope and next-generation ground-based telescopes will play a crucial role in identifying these elusive events and capturing data that could unlock their secrets. Researchers are also exploring ways to link LFBOT detections with other cosmic signals, such as gravitational waves, which could provide additional clues about what is causing these explosions. If LFBOTs are connected to collisions between compact objects, such as neutron star mergers, then they could be an important piece of the puzzle in understanding how the most extreme astrophysical systems evolve over time. While many questions remain unanswered, one thing is certain: LFBOTs are rewriting the rules of high-energy astrophysics. These enigmatic explosions are forcing scientists to rethink fundamental concepts about how stars die, how black holes form, and how energy is released in the most extreme environments in the universe. Whether they turn out to be a new class of astrophysical event, a missing link between known phenomena, or something entirely unexpected, LFBOTs represent one of the most thrilling mysteries in modern science. With every new discovery, astronomers are getting closer to unraveling the true nature of LFBOTs. The answers may lie in the next detection, the next observation, or the next breakthrough in theoretical physics. Until then, these luminous fast blue optical transients will continue to challenge our understanding of the cosmos, reminding us that the universe still holds countless secrets waiting to be uncovered. LFBOTs remain a fascinating enigma in astrophysics, pushing the boundaries of what we know about extreme cosmic events. Each new discovery challenges our existing models, suggesting that these explosions may be more diverse and complex than we ever imagined. The fact that they do not fit neatly into known categories, such as supernovae, gamma-ray bursts, or tidal disruption events, suggests that they could be part of a broader spectrum of high-energy astrophysical phenomena that are still poorly understood. One of the biggest challenges in studying LFBOTs is their fleeting nature. Unlike supernovae, which gradually brighten over weeks and linger for months, LFBOTs reach their peak brightness within a few days and fade quickly. This makes them incredibly difficult to capture in real time. By the time astronomers detect them, much of the crucial early-stage data is already lost. This has led to a race to develop faster detection methods, using artificial intelligence and automated sky surveys to catch these events as they happen. Telescopes such as the Zwicky Transient Facility, CTF, and the Vera-C. Rubin Observatory are expected to revolutionize our ability to detect LFBOTs, allowing astronomers to gather more detailed data on their properties and behavior. One of the most puzzling aspects of LFBOTs is their energy output. These explosions emit immense amounts of energy in a very short period, rivaling some of the most powerful known cosmic events. Yet, they do not seem to be associated with the processes that usually produce such high-energy emissions, such as the collapse of massive stars or the merger of neutron stars. This raises an intriguing question: what kind of astrophysical engine could power such a rapid and intense burst of energy? Some theories suggest that LFBOTs could be linked to the formation of exotic objects, such as quark stars, hypothetical ultra-dense stars made of free quarks, which have never been directly observed. Others propose that LFBOTs could be the result of failed supernovae, where a star collapses directly into a black hole without producing the kind of explosion we would normally expect. Another possibility is that LFBOTs are connected to interactions between compact objects, such as neutron stars and black holes, in ways that have not yet been considered. For example, if a neutron star were to collide with a white dwarf or another neutron star under specific conditions, it might produce a short-lived but extremely luminous explosion. This could explain why LFBOTs appear in unusual locations, far from the dense star-forming regions where most supernovae occur. If these events are being triggered by rare interactions between stellar remnants, it would suggest that our understanding of how compact objects evolve and interact is incomplete. One of the most significant clues about LFBOTs comes from their strange afterglows. Unlike typical supernovae, which fade in a predictable manner, LFBOTs exhibit unusual behavior in multiple wavelengths. Their radio emissions persist long after the optical light has disappeared, indicating that they may be producing powerful shockwaves that continue interacting with their surroundings for an extended period. This behavior is reminiscent of gamma-ray bursts, which produce afterglows as their relativistic jets plow through interstellar space. However, LFBOTs differ in key ways, suggesting that if they do involve jets, these jets are operating in an entirely new regime. The possibility that LFBOTs are linked to unknown forms of matter or new physics cannot be ruled out. Some researchers have speculated that these explosions could be tied to the breakdown of exotic particles or the release of energy from processes that go beyond the standard model of physics. If true, LFBOTs could provide a unique window into the fundamental forces that govern the universe, offering insights into dark matter, quantum gravity, or even the nature of space-time itself. As more LFBOTs are detected, astronomers hope to uncover patterns that will help classify these events and reveal their origins. Are they all produced by the same mechanism, or do they represent multiple distinct processes that happen to share similar observational properties? Do they always occur in isolated regions, or will future observations reveal that they can also appear in dense galactic environments? These are just some of the questions that remain unanswered. One of the most exciting aspects of studying LFBOTs is the potential for unexpected discoveries. Every time a new transient event is observed, it has the potential to rewrite our understanding of the cosmos. LFBOTs are a perfect example of this. When the first ones were discovered, they did not fit any known category, forcing scientists to rethink their models of stellar evolution, black hole formation, and high-energy astrophysics. If history is any guide, the study of LFBOTs will likely lead to new insights that extend far beyond these mysterious explosions themselves. For now, LFBOTs remain one of the greatest unsolved puzzles in astronomy. Their rapid appearance and disappearance, their immense energy output, and their bizarre locations all point to an underlying process that has yet to be fully understood. With the next generation of telescopes and detection systems, scientists are on the verge of uncovering the secrets of these enigmatic events. Whether they turn out to be a new class of supernova, a missing link between different cosmic explosions, or something entirely unexpected, one thing is certain: LFBOTs are a reminder that the universe is far more complex and mysterious than we ever imagined. The search for answers continues, and with each new discovery, we move closer to unlocking one of the most intriguing astrophysical mysteries of our time. LFBOTs represent one of the most tantalizing astrophysical mysteries of our time, not only because of their extreme luminosity and rapid evolution but also due to the sheer number of unanswered questions surrounding them. Their unpredictability makes them a challenge for astronomers, but also a potential goldmine for new discoveries that could reshape our understanding of cosmic events. Every time a new LFBOT is observed, it provides more data that might eventually allow scientists to piece together the puzzle. Yet, despite numerous observations, these transient bursts refuse to conform to any existing models, forcing researchers to rethink what they know about explosive cosmic phenomena. One of the most intriguing aspects of LFBOTs is the sheer speed at which they brighten and fade. Traditional supernovae follow a predictable pattern, gradually increasing in brightness over weeks and then slowly dimming over months. LFBOTs, on the other hand, appear suddenly, peak in just a few days, and then disappear just as quickly, with only lingering afterglows and radio and other wavelengths providing clues about their nature. This extreme rapidity suggests that whatever is driving LFBOTs must be an exceptionally efficient and explosive process. But what could cause such an instantaneous release of energy? One hypothesis is that LFBOTs could be related to Magnetars, a rare type of neutron star with an incredibly powerful magnetic field. Magnetars are already known to produce some of the most extreme bursts of energy in the universe, including fast radio bursts, FRBs, and soft gamma-ray repeaters. Some scientists suspect that under the right conditions, a magnetar could undergo a catastrophic event that produces an LFBOT-like explosion. This could happen if the magnetar experiences a sudden collapse, releasing a vast amount of energy in an incredibly short time. The problem with this theory, however, is that LFBOTs do not appear in regions where we expect to find magnetars. Most are located in isolated environments far from star-forming regions. This raises another important question: if magnetars are responsible for LFBOTs, why are they appearing in such unexpected places? Another potential explanation for LFBOTs is that they are related to failed supernovae, events where a massive star collapses directly into a black hole without producing the kind of explosion we normally associate with stellar deaths. In a typical supernova, the collapse of a massive star triggers an outward shockwave that violently expels the star's outer layers into space. However, in some cases, the collapse might be so extreme that most of the star's material falls directly into the black hole, producing only a brief but incredibly intense burst of light before disappearing entirely. This could explain why LFBOTs fade so quickly and why they do not leave behind the kind of long-lasting remnants we associate with normal supernovae. Yet, even this theory does not fully explain the strange properties of LFBOTs. One of the most unusual features of these explosions is the presence of long-lasting radio emissions, which suggests that something is continuing to interact with the surrounding space long after the initial burst of light has faded. In normal supernovae, this kind of radio emission is produced when the expanding shockwave from the explosion collides with the surrounding interstellar medium. However, the radio signals from LFBOTs are far stronger than expected, leading some researchers to propose that these events might involve jets, highly collimated streams of material moving at nearly the speed of light. Jets are a common feature of many high-energy astrophysical events, including gamma-ray bursts, grbs, and active galactic nuclei (AGN). If LFBOTs do involve jets, this would suggest that they might be related to a completely different type of process, perhaps the sudden activation of a dormant black hole, or the collision of two compact objects such as neutron stars. The presence of jets would also help explain why LFBOTs are so luminous, as relativistic jets are capable of amplifying energy output through a process known as Doppler boosting. However, detecting these jets is difficult, as they must be oriented in just the right way for us to observe them directly. One of the most perplexing observations regarding LFBOTs is their unusual locations within galaxies. Unlike supernovae, which tend to occur in regions of active star formation, LFBOTs have been found in unexpected places, often in the outskirts of galaxies or even in completely isolated environments. This suggests that whatever is causing LFBOTs is not linked to young, massive stars, the kind that typically produce supernovae, but rather to an entirely different population of objects. This has led to speculation that LFBOTs might be connected to old, evolved stars or to compact remnants such as black holes, neutron stars, or even white dwarfs undergoing rare and extreme interactions. Another mystery surrounding LFBOTs is their peculiar color. Most astrophysical explosions emit light across a wide range of wavelengths, but LFBOTs are dominated by an intense blue optical signal, indicating extremely high temperatures. This is where their name comes from: luminous fast blue optical transients. The challenge is that there are very few known astrophysical processes capable of producing such a bright and short-lived blue flash. Even some of the most extreme types of supernovae, such as parainstability supernovae or hypernovae, do not match the characteristics of LFBOTs, leaving researchers puzzled about what could be generating this intense burst of blue light. Some astronomers have suggested that LFBOTs might be linked to unusual forms of matter, such as strange quark matter, an exotic phase of matter that could exist under extreme conditions. If an LFBOT represents the sudden conversion of a neutron star into a quark star, this could produce a rapid and extremely luminous explosion unlike anything seen before. However, quark stars remain purely theoretical, and there is no direct evidence that they exist in nature. If LFBOTs do turn out to be connected to quark stars, they could provide the first real observational proof of this exotic form of matter. As more data is collected, it is likely that LFBOTs will either be classified into a new category of cosmic explosions or will turn out to be multiple different phenomena that just happen to share similar observational properties. Either way, studying LFBOTs is forcing astronomers to rethink some of the most fundamental aspects of high-energy astrophysics, including how stars die, how black holes form, and what kinds of extreme processes can occur in the universe. One of the most exciting aspects of LFBOT research is the potential for completely unexpected discoveries. Every time astronomers point their telescopes at the sky, they have the chance to observe something never seen before, and LFBOTs are a perfect example of how the universe continues to surprise us. With the next generation of telescopes and space observatories, such as the Vera C. Rubin Observatory and the James Webb Space Telescope, astronomers hope to capture LFBOTs in greater detail than ever before. These future observations may finally reveal the true nature of these mysterious explosions and unlock a new chapter in our understanding of the cosmos. For now, the mystery of LFBOTs remains unsolved, and every new detection brings both answers and new questions. The rapid bursts of blue light, the unexpected locations, the powerful afterglows, Each piece of the puzzle suggests that something truly extraordinary is happening out there in the universe. Whether they are the signatures of newborn black holes, failed supernovae, or something even more exotic, LFBOTs are a reminder that we still have so much to learn about the violent and unpredictable nature of the cosmos. LFBOTs are among the most perplexing astronomical events ever recorded. They challenge our fundamental understanding of how high-energy cosmic explosions work, and despite years of study, they refuse to fit neatly into any existing category. Their intense brightness, rapid appearance, and unusual locations make them an astrophysical anomaly, pushing scientists to rethink established theories about stellar deaths, black hole formations, and even the physics of extreme matter. With each new detection, the mystery deepens, leaving behind more questions than answers. One of the most baffling aspects of LFBOTs is their ability to emit light across multiple wavelengths, from optical to ultraviolet, and even radio. The high-energy nature of these explosions suggests that they involve an incredibly violent process, but what exactly triggers them remains unknown. Some researchers suspect that LFBOTs might be the result of highly magnetized neutron stars, Magnetars, undergoing a sudden and catastrophic transformation. Others believe they could be related to black hole activity, possibly involving matter falling into an accretion disk at just the right angle to produce an ultraluminous burst. But neither of these theories fully explains the strange behavior of LFBOTs. A major clue comes from the discovery of persistent radio signals associated with some LFBOTs. These signals indicate that whatever is causing these explosions continues to interact with the surrounding environment long after the initial flash has faded. This is not typical of supernovae, which release their energy in a single explosive event and then gradually fade away. The fact that LFBOTs leave behind detectable afterglows suggests that they involve either highly energetic jets or a sustained energy source, similar to the aftermath of a neutron-star merger. The problem is that LFBOTs do not match the expected locations of neutron-star collisions, leaving scientists without a clear answer. One of the strangest aspects of LFBOTs is how they appear in parts of galaxies where we would not expect to see high-energy explosions. Typically, the most energetic cosmic events, such as supernovae and gamma-ray bursts, occur in regions where massive stars are forming, since these stars eventually explode at the end of their lives. But LFBOTs seem to defy this pattern. Instead of appearing in dense star-forming regions, they have been found in the outskirts of galaxies, in locations where star formation is minimal. This raises the question, what kind of objects are exploding if they are not massive stars in their final moments? Another peculiar trait of LFBOTs is their extreme temperatures. They shine brightly in the blue optical range, indicating that they are incredibly hot, much hotter than typical supernovae. Theories that involve shockwaves or jets struggle to explain this intense heat, leading some researchers to consider more exotic possibilities. One possibility is that LFBOTs are powered by the sudden collapse of a neutron star into a quark star, a hypothetical form of matter that exists at densities even greater than those found in neutron stars. If such a transition occurs, it could theoretically release an immense amount of energy in a very short time, matching the observed properties of LFBOTs. Despite all these theories, LFBOTs remain frustratingly difficult to classify. Unlike supernovae, they do not leave behind large amounts of debris or expanding remnants. Unlike gamma-ray bursts, they are not accompanied by the characteristic high-energy gamma-ray emissions. Unlike tidal disruption events, where a star is torn apart by a black hole, LFBOTs do not seem to occur near the centers of galaxies where supermassive black holes reside. Every new piece of data only seems to make the mystery more complex, rather than providing a clear explanation. Astronomers are now focusing on trying to catch LFBOTs in action as they happen, using next-generation observatories capable of scanning the sky for transient events. The Vera C. Rubin Observatory, expected to begin operations soon, may provide crucial insights by detecting LFBOTs at an earlier stage than ever before. If scientists can observe the very first moments of an LFBOT explosion, they might be able to determine whether it originates from a collapsing star, a merging compact object, or something entirely unexpected. The discovery of LFBOTs serves as a reminder that the universe is still full of surprises. Every time astronomers believe they have a comprehensive understanding of cosmic explosions, something new emerges that challenges their assumptions. LFBOTs may represent an entirely new class of astrophysical events, one that requires a fundamental shift in our understanding of how matter behaves under extreme conditions. If scientists can unlock the secrets behind these mysterious bursts, they may gain insights into not just stellar deaths, but also the formation of black holes, the nature of neutron stars, and even the possibility of exotic states of matter that have never been observed before. As telescopes become more advanced and our ability to detect transient events improves, the hope is that we will soon gather enough data to solve the mystery of LFBOTs once and for all. Until then, these strange, fleeting bursts of blue light will continue to be one of the most intriguing unsolved puzzles in modern astrophysics. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.